In the autumn of 2019, something entered our solar system that had never been here before. Not in the 4.5 billion years since the planets formed. Not in the hundreds of millions of years since complex life first emerged on Earth. Not once in the entire span of recorded human civilization. It came from the dark between the stars. It arrived silently, without warning, moving so fast that our sun's gravity, the same force that holds 8 planets, hundreds of moons, and billions of asteroids in its relentless grip, could not even slow it down. This object had no name when it first appeared as a faint smudge on the instruments of a single amateur astronomer working in Crimea. It was barely visible, a ghost against the black, but within weeks, every major telescope on Earth had swung toward it. Within months, the Hubble Space Telescope, orbiting 540 kilometers above the planet, was tracking it from space. And within a year, what scientists found hiding inside that faint smudge would challenge fundamental assumptions about where comets come from, what they carry inside their ancient ice, and what it means to receive a visitor from a place no human will ever see. Its official designation is 2I/Borisov. The 2I marks it as the second confirmed interstellar object ever detected by humanity. The first, a bizarre elongated rock called Oumuamua, had blazed through our solar system just 2 years earlier, in 2017, moving at a speed and angle that could only mean one thing: it was not from here. It was spotted only after it had already passed its closest point to the Sun, hurtling away before anyone could study it properly. Oumuamua left behind more questions than answers, and some of those questions pushed into territory usually reserved for science fiction. Was it a fragment of a shattered planet? A shard of frozen nitrogen torn from an alien Pluto? A light sail from another civilization, as one Harvard astronomer controversially suggested? Nobody could say. The data was too sparse, the observation window too brief, and then it was gone forever. But Borisov was different. Borisov was spotted on its way in. For the first time in the history of our species, we had advance warning that something from another star system was about to pass through our cosmic neighborhood. For the first time, we could watch it approach, plan our observations, and aim our most powerful instruments directly at it while it was still close enough to study. The world's great observatories mobilized. The William Herschel telescope in the Canary Islands turned toward it. The Gemini Observatory in Hawaii locked on. The Very Large Telescope in Chile's Atacama Desert, sitting high in the driest place on Earth, pointed its array of mirrors at this tiny, ancient traveler. And high above all of them, the Hubble Space Telescope captured images so crisp that scientists could begin estimating the size and shape of the solid nucleus hidden inside the comet's glowing shroud of gas. What they found was both deeply reassuring and profoundly strange. Reassuring because Borisov looked, at first glance, like a comet, a familiar type of object, the kind we have studied for centuries. It had a fuzzy coma, a cloud of gas and dust surrounding its solid core. It had a tail swept back by the solar wind, faintly luminous. In many ways, it resembled the comets we know from our own solar system. It looked ordinary, almost unremarkable. But here is the problem. The deeper scientists looked, the stranger Borisov became. Its chemical composition was wrong, not wildly alien, not unrecognizable, but subtly and disturbingly off. The ratio of carbon monoxide to water in its outgassing was unlike any comet ever measured in our solar system. The amount of carbon monoxide pouring off its surface was extraordinary, far more than solar system comets produce at a similar distance from the Sun. Its nucleus appeared pristine, as though it had never been heated before, as though it had spent its entire existence in the frozen dark between stars, untouched and unchanged, since the moment it first condensed from a cloud of gas and dust orbiting a star we cannot name. And locked inside that ancient ice was a chemical record of a world we will never visit, a fingerprint of a planetary system whose star we have not identified, a frozen archive from a time and place separated from us by light years of empty space and possibly billions of years of cosmic history. Every molecule in Borisov's ice was a clue. Every atom was a witness to conditions that existed around a distant star, in a distant era, in a corner of the galaxy that no human eye has ever seen up close. And those clues, when scientists finally decoded them, did not tell the comfortable story that anyone expected. By the end of tonight, you are going to understand what Borisov really was. where it likely came from, and why its chemical secrets are rewriting our understanding of how planetary systems form across the galaxy. You are going to understand why some scientists now believe that the space between stars is not empty at all, but is teeming with trillions upon trillions of these frozen wanderers, each one a remnant of a world that may no longer exist, each one carrying a chemical autobiography written in ice and dust and ancient molecular bonds. And you are going to understand why that revelation, if it holds, changes everything we thought we knew about the galaxy we live in and about our own place within it. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. To understand why Borisov shook the foundations of cometary science, we need to start with what a comet actually is, and how every comet humanity had ever studied, until Borisov came from the same place we do. For most of human history, comets were omens. They appeared without warning, hung in the sky for days or weeks like glowing swords or spectral fingers, and vanished just as suddenly. The Babylonians recorded them on clay tablets as portents of royal death and military defeat. The Chinese meticulously catalogued them in astronomical records spanning thousands of years, noting their positions, brightness, and the length of their tails with remarkable precision. In 44 BC, a brilliant comet appeared over Rome in the weeks following the assassination of Julius Caesar, and the Roman Senate declared it to be Caesar's soul ascending to the heavens, the divine confirmation of a dictator's godhood. In 1066, Halley's comet blazed across the English sky just months before the Norman invasion, and the Bayeux tapestry, woven to commemorate William the Conqueror's victory, depicts the comet hovering ominously over a crowd of terrified onlookers, their fingers pointing upward in dread. But comets are not omens. They are not divine messages or celestial warnings. They are something far more interesting. They are leftovers. When our solar system formed, roughly 4.6 billion years ago, it began as an enormous cloud of gas and dust, a rotating disk of material surrounding a newborn star. This disk was vast, spanning hundreds of astronomical units from edge to edge, and it contained everything that would eventually become the Sun, the planets, the moons, the asteroids, and the comets. Most of that material was pulled inward by gravity. It clumped together, accreted, collided, merged. Close to the Sun, where temperatures were high, rocky material survived: silicates, metals, iron, and these built the terrestrial planets: Mercury, Venus, Earth, Mars. Farther out, beyond a boundary called the frost line, it was cold enough for water to freeze into solid ice, and these icy grains combined with rock to build the cores of the giant planets: Jupiter, Saturn, Uranus, Neptune. But not everything got used. Not by a long distance. At the outermost edges of the disk, trillions of small icy bodies formed and then simply stayed there. They were too far from the Sun to be warmed, too small to be pulled into any planet, too distant to be disturbed by anything. They lingered in the deep cold, frozen in place like artifacts in a museum, preserved in temperatures just a few degrees above absolute zero. Over billions of years, they remained essentially unchanged, time capsules from the very birth of the solar system. These icy remnants became what we now call the Oort cloud, a vast, roughly spherical shell of frozen debris that surrounds our solar system at an almost incomprehensible distance. Named after the Dutch astronomer who first proposed its existence, the Oort cloud is the most remote structure associated with our Sun, a ghostly halo of ancient ice that no human instrument has ever directly imaged and no spacecraft will reach for centuries. The Oort cloud begins at roughly 2,000 astronomical units from the Sun and extends outward to perhaps 100,000 astronomical units. To put that distance in perspective, 1 astronomical unit is the distance from the Earth to the Sun, approximately 93 million miles, or 150 million kilometers. The outer edge of the Oort cloud, then, is roughly 100,000 times farther from the Sun than we are. If you could somehow drive a car at highway speed toward the outer Oort cloud, it would take you more than 1.5 trillion years to arrive. The current age of the universe, 13.8 billion years, would not be nearly enough time. If the entire solar system, from the Sun to Neptune, were shrunk to the size of a small coin sitting on a desk, the Oort cloud would be a sphere the size of a stadium surrounding that desk. We live, in cosmic terms, at the very center of an enormous and invisible vault of ancient ice. No one has ever directly observed the Oort cloud. No telescope has ever imaged it. No spacecraft has come anywhere close. Voyager 1, the most distant human-made object, launched in 1977 and now more than 155 astronomical units from the Sun, has not even reached 1% of the distance to the Oort cloud's inner edge. At its current speed of roughly 17 kilometers per second, Voyager 1 will not reach the Oort cloud for another 300 years. It will not pass through it for another 30,000 years. The scale is beyond human intuition. We know the Oort cloud exists because, every now and then, something from out there gets knocked loose. A passing star drifts close enough to disturb the gravitational balance. The galactic tide, the combined gravitational pull of all the mass in the Milky Way, distributed unevenly across the galactic disk, exerts a subtle but persistent torque on the outermost Oort cloud objects, slowly reorienting their orbits over millions of years. Occasionally, a molecular cloud, a dense clump of interstellar gas and dust, passes near the solar system, adding its own gravitational perturbation to the mix. Any of these influences can nudge an Oort cloud object just enough to send it tumbling inward on a journey toward the Sun, a journey that can take 1 million, 5 million, even 10 million years to complete. The concept of the Oort cloud was first proposed in 1950 by the Dutch astronomer Jan Oort. He noticed that long-period comets with orbital periods of thousands or millions of years, seemed to arrive from all directions in the sky, with no preference for the plane of the solar system. This was puzzling. If comets came from the Kuiper belt, or from the plane of the planets, they should arrive predominantly from directions near that plane. Instead, they came from everywhere, above, below, ahead, behind, as if they were falling in from a spherical shell surrounding the Sun. Oort proposed exactly that. A vast spherical reservoir of icy bodies, extending to enormous distances, from which comets are occasionally dislodged and sent inward. The idea was elegant, simple, and consistent with the data. It has remained the standard model for the origin of long-period comets ever since. The number of objects in the Oort cloud is estimated to be in the trillions, perhaps 2 trillion objects larger than 1 kilometer, with many more smaller bodies below that threshold. The total mass is harder to pin down, but estimates generally range from 1 to a few tens of Earth masses. This vast population of icy bodies represents the scattered remnants of the solar system's formation, objects that were gravitationally ejected from the inner solar system by interactions with the giant planets, primarily Jupiter and Saturn, and ended up stranded in the cold, distant periphery. When one of these Oort cloud objects finally arrives in the inner solar system after its million-year journey, the Sun's heat begins its transformation. The surface ice sublimes, transitions directly from solid to gas, and streams of vapor carry dust particles outward, forming the fuzzy luminous coma that surrounds the solid nucleus. The solar wind and radiation pressure sweep this material backward, stretching it into the long, elegant tail that has captivated humans since the dawn of civilization. And for a few weeks or months, we see it as a comet, a fleeting visitor from the deep freeze, briefly warming itself by the fire before retreating back into the cold. This is the origin of every long-period comet we have ever observed. Halley's Comet, which returns every 75 to 79 years, and has been recorded by humans since at least 240 BC. Comet Hale-Bopp, which dazzled observers in 1997 with a nucleus estimated at 40 kilometers across, roughly the distance from one end of a major city to the other, trailing a dust tail and an ion tail that stretched across the night sky for months. Comet Hyakutake, which passed within just 15 million kilometers of Earth in 1996, making it one of the closest cometary approaches in centuries. Comet McNaught, which became so bright in January of 2007 that it was visible in broad daylight to observers in the southern hemisphere. Comet Neowise, which graced the skies during the summer of 2020. A rare naked-eye comet that gave millions of people lockdown during global pandemic, a reason to step outside and look upward. Every one of them is a piece of our own solar system's ancient construction debris, finally drifting inward from the Oort cloud after billions of years in cold storage. And every one of them carries, frozen in its ancient ice, a chemical record of the conditions that existed in the primordial solar nebula 4.6 billion years ago. Before the Earth had formed, before the Moon existed, before the oceans condensed, before the first microbes stirred in the warm shallows of a young planet. Comets are time capsules. They are the oldest, most pristine objects accessible to human study. And for centuries, every one we had ever examined came from the same cosmic neighborhood. They were all ours. The importance of this fact cannot be overstated. When scientists studied the chemical composition of solar system comets, the ratios of water to carbon dioxide, the abundances of methane and ammonia and hydrogen cyanide, the isotopic ratios of hydrogen and nitrogen, they were reading a record of our own origins. The chemistry of comets told us about the temperature structure of the primordial solar nebula. It told us about the radiation environment around the young sun. It told us how far from the star different molecular species could survive in solid form. Every measurement was a data point in the story of how our solar system was built. And because every comet came from the same system, every data point belonged to the same story. There was no external reference, no comparison, no way to know whether our solar system's cometary chemistry was typical or unusual, ordinary or extraordinary, because we had never seen a comet from anywhere else. There is also a second, closer reservoir, the Kuiper Belt, a broad ring of icy bodies stretching from just beyond Neptune's orbit at about 30 astronomical units, out to roughly 50 astronomical units from the Sun. This is where Pluto lives, reclassified from planet to dwarf planet in 2006, a decision that remains controversial to this day, but that reflects the reality that Pluto is not alone out there. It is one member of a vast population of icy worlds. The Kuiper Belt is home to hundreds of thousands of objects larger than 100 kilometers in diameter, and millions more that are smaller. Some, like Eris and Makemake, are almost as large as Pluto itself. Others are tiny, irregular fragments of ice and rock barely a few kilometers across. Together, they represent the leftovers of the outer solar system's formation, material that never got incorporated into a planet, stranded in the cold dark beyond Neptune's gravitational reach. This is also where the short-period comets originate. Comets that orbit the Sun on relatively brief timescales, every few years or decades, compared to the millennia-long orbits of Oort cloud comets. The most famous example is Comet Churyumov-Gerasimenko, also known as 67P, a small, oddly shaped comet about 4 kilometers across that looks like a rubber duck. Two rounded lobes connected by a narrow neck. In 2014, the European Space Agency's Rosetta spacecraft arrived at this comet after a 10-year journey through the solar system. Rosetta orbited Churyumov-Gerasimenko for more than 2 years, photographing its surface in extraordinary detail, analyzing its outgassing, measuring the isotopic composition of its water, and even deploying a small lander called Philae onto its surface. The first time a spacecraft had ever landed on a comet, the data from Rosetta transformed our understanding of cometary science. It revealed a world of cliffs and boulders, sinkholes and jets, a landscape shaped by the slow sublimation of ice over countless orbits around the Sun. But Rosetta studied a local comet, a comet born in our Kuiper Belt, made from the same primordial material as our Sun and our Earth. Every molecule Rosetta measured, every isotope it catalogued, every dust grain it analyzed, belonged to our own solar system. There was no way to compare it to comets from elsewhere, because no comet from elsewhere had ever been identified. Here is the point that matters for our story. Every comet humanity had ever studied, from the ancient Babylonian records carved into clay to the samples collected by Rosetta and Stardust, and the other great cometary missions of the space age, formed inside our own solar system. They were our comets. They condensed from the same primordial disk of gas and dust that built the Sun, the Earth, the Moon, and every asteroid, every meteorite, every grain of cosmic dust we have ever analyzed. Their chemical compositions, while diverse, all fell within a recognizable family range. Variations on a single theme, ingredients from the same cosmic pantry. We had an extensive catalogue of cometary chemistry, and every entry in that catalogue came from the same address. And then along came Borisov, and everything changed. To understand how the discovery happened, we need to meet the man who made it. Gennady Borisov is not a professional astronomer employed at a research university or a national space agency. He does not have access to billion-dollar facilities. He is an amateur astronomer, passionate, methodical, and deeply skilled, based at the Margot Observatory in Nauchny, a small settlement in Crimea's Bakhchisarai district. His primary instrument is a telescope he designed and built himself, with a primary mirror just 65 centimeters in diameter. That is tiny by professional standards. The twin Keck telescopes on Mauna Kea in Hawaii each have mirrors 10 meters across, more than 15 times wider than Borisov's mirror, capturing roughly 237 times more light. The James Webb Space Telescope, orbiting at the Sun-Earth Lagrange 2.1 million kilometers from our planet, has a primary mirror 6.5 meters in diameter, composed of 18 hexagonal gold-coated beryllium segments. Borisov's telescope could fit inside a large closet. It is the kind of instrument that professional astronomers might overlook entirely. But Gennady Borisov was not trying to compete with billion-dollar observatories. He was doing something deceptively simple and critically important. Something that does not require a massive mirror, but does require extraordinary patience and attention to detail. He was scanning the sky night after night, looking for objects that moved. In the arena of moving object detection, aperture is less important than persistence, cadence, and skill. Asteroids and comets reveal themselves by their motion. They drift across the background of fixed stars over hours or days, and a trained observer with the right equipment and the right software can spot them as tiny points of light that shift position between successive images. On the morning of August 30th, 2019, Borisov was conducting one of his routine surveys when he noticed something. A faint point of light had shifted against the background stars in a way that did not correspond to any object in the known catalogues. He measured its position precisely. He noted its brightness and the rate of its motion. He checked the ephemerides, the predicted positions of known asteroids and comets. No match. The object was new and its motion was unusual. It was not tracing the gentle, predictable arc of an object in a standard elliptical orbit around the Sun. The trajectory was steeper, faster, more extreme. Something about this object's path through space did not fit the patterns of any solar system body, and Gennady Borisov, who had been scanning the skies long enough to recognize what normal looked like, knew that this was not normal. Within days, he submitted his observations to the Minor Planet Center, the international clearinghouse run under the auspices of the International Astronomical Union for the tracking and cataloguing of newly discovered solar system objects. Professional astronomers around the world received the alert and immediately turned their own instruments toward the reported coordinates. Confirmation came swiftly. The object was real. It was moving exactly as Borisov had reported, and its orbit, when calculated from the accumulating positional measurements, was hyperbolic. A hyperbolic orbit is the telltale signature of an interstellar interloper. Most objects in the solar system travel on elliptical orbits, closed loops that bring them around the Sun and back again, over and over. Some orbits are nearly circular, like Earth's. Some are highly elongated, like those of long-period comets. But all elliptical orbits are closed. They are gravitationally bound to the Sun. A hyperbolic orbit, by contrast, is open. It curves through the solar system without ever closing on itself. An object on a hyperbolic trajectory is not bound to the Sun. It is passing through, gaining energy from the gravitational slingshot, and it will never return. It came from somewhere else, and it is going back to somewhere else, accelerating outward until the Sun's gravity becomes negligible, and the object resumes its lonely drift through the galaxy. Borisov's velocity relative to the Sun was approximately 32 kilometers per second, roughly 71,000 miles per hour. To put that in perspective, the International Space Station orbits Earth at about 7.7 kilometers per second. A bullet fired from a high-powered rifle travels at roughly 1 kilometer per second. Borisov was moving more than 30 times faster than a bullet, and it was far too fast to have originated from any known mechanism within our solar system. No gravitational slingshot around Jupiter, no encounter with a passing star, no conceivable perturbation could have accelerated a local body to that speed on that trajectory. The conclusion was inescapable and electrifying. This object had entered our solar system from interstellar space. The International Astronomical Union designated it C/2019 Q4 Borisov, and later formally redesignated it 2I/Borisov, the 2I prefix officially marking it as the second interstellar object ever identified by humans. The I stands for interstellar, a designation category that did not even exist until Oumuamua forced the International Astronomical Union to create it in 2017. Before Oumuamua, there was no official system for naming objects that came from outside our solar system, because no one had ever needed one. The creation of the I designation was itself a milestone, a quiet acknowledgement that the cosmos had delivered something humanity had never dealt with before. The first 1I/Oumuamua had been discovered 2 years earlier, in October 2017, by the Pan-STARRS 1 telescope in Hawaii, a survey instrument designed specifically to scan the entire visible sky repeatedly, looking for transient events, moving objects, and anything that changed. But the differences between the two discoveries were dramatic and scientifically crucial. They are worth examining in some detail because they define the context into which Borisov arrived and explain why the scientific community responded to it with such intensity and coordination. Oumuamua had been found only after it had already swung past the Sun and was racing away. The Pan-STARRS telescope detected it on October 19, 2017, when it was already 33 million kilometers from Earth and receding fast. Astronomers had just a few frantic weeks to study it before it faded beyond detection, shrinking from a faint point of light to an undetectable ghost in the background noise of the sky. The data they collected during that narrow window was sparse, fragmentary, and maddeningly ambiguous. Most troubling of all, Oumuamua showed no coma, no tail, no visible outgassing. All the defining hallmarks of a comet were absent. This made it appear to be a bare asteroid, a naked rock tumbling through the void without any ice on its surface. Yet its trajectory showed a slight but measurable, non-gravitational acceleration, a push away from the Sun that could not be fully explained by gravity or solar radiation pressure alone. For a comet, such acceleration is routine. The jet-like force of outgassing acts like a tiny rocket, pushing the comet slightly off its purely gravitational trajectory. But if Oumuamua was not outgassing, where was the push coming from? Its shape only deepened the mystery. Based on the way its brightness varied as it tumbled, brightening and dimming in a regular pattern, astronomers inferred that it was wildly elongated, perhaps 6 to 10 times longer than it was wide. No known natural object in our solar system has such extreme proportions. The shape fueled speculation that ranged from the exotic to the outlandish. Harvard astrophysicist Avi Loeb publicly proposed that Oumuamua might be an artifact of extraterrestrial technology, perhaps a discarded light sail pushed through space by the radiation pressure of its parent star. Other scientists proposed more naturalistic explanations. A shard of frozen nitrogen ripped from the surface of an exo-Pluto, a fragment of a disrupted comet, a cosmic dust bunny held together by electrostatic forces. None of these explanations were fully satisfying. None could account for all the observed properties simultaneously, and by the time the debate was in full swing, Oumuamua was already too distant to observe. It had vanished, taking its secrets with it. Borisov arrived into a scientific community that was desperate for a second chance. And this time, fate was generous. Borisov was detected months before its closest approach to the Sun, which would not occur until December 8, 2019. This gave astronomers something they had never had with an interstellar object: a runway. They could plan observations weeks in advance. They could submit proposals for time on the Hubble Space Telescope, a process that normally takes months of competitive review but was fast-tracked given the unprecedented nature of the target. They could coordinate multi-wavelength campaigns spanning radio, infrared, optical, and ultraviolet observations across dozens of observatories on multiple continents. They could watch this visitor approach the Sun, swing around it, and recede into the outer solar system, a complete observational arc that Oumuamua had cruelly denied them. And they moved fast. The response from the global astronomical community was immediate and coordinated. Within days of the confirmed interstellar classification, telescopes on every continent were swinging toward Borisov's position. The William Herschel telescope, perched atop the volcanic island of La Palma in the Canary Islands, captured some of the first detailed spectra of the comet's coma, breaking its faint light into the rainbow of wavelengths that reveal molecular composition. The Gemini North Telescope on Mauna Kea in Hawaii, sitting nearly 14,000 feet above sea level, where the atmosphere is thin and dry, obtained high-resolution images that tracked the evolution of the coma's structure. The Very Large Telescope, actually a suite of 4 individual 8.2-meter telescopes at the European Southern Observatory's Paranal site in Chile's Atacama Desert, one of the driest, darkest, and most atmospherically stable observing locations on Earth, turned its immense light-gathering power toward this tiny, ancient traveler. The Apache Point Observatory in New Mexico contributed spectroscopic data. The Neil Gehrels Swift Observatory, an orbiting spacecraft designed primarily for detecting gamma-ray bursts, was repurposed to observe Borisov in ultraviolet wavelengths. And the crown jewel of the campaign, the Hubble Space Telescope, orbiting 540 kilometers above the Earth's atmosphere, free from the twinkling and blurring that plague ground-based observations, captured a series of images so sharp that scientists could resolve features within the coma just a few hundred kilometers across. These images revealed the compact, bright central condensation that marked the position of the solid nucleus, surrounded by the expanding shell of gas and dust that was being steadily boiled off its surface by the sun's heat. Polarimetric observations added another dimension. By measuring how sunlight was polarized, how its electromagnetic waves were oriented, after scattering off the dust grains in Borisov's coma, astronomers could infer the physical properties of those grains, their average size, their shape, their porosity, and their composition. This technique, applied systematically across multiple wavelengths, built a picture of Borisov's dust that would later prove to be one of the most revealing and puzzling aspects of the entire dataset. And what emerged from that portrait was a revelation that would reshape the field. The reassuring parts first. Borisov had a coma, a fuzzy, luminous cloud of gas and dust surrounding the solid nucleus. It had a tail, fanning out behind it as the solar wind pushed sublimated material away from the sun. It was actively outgassing, releasing water vapor, dust, and various volatile compounds as the sun's heat penetrated its surface ice and turned solid directly to gas. Its nucleus was estimated at roughly 1 kilometer in diameter, perhaps slightly less. Small but well within the range of known solar system comets. If you had looked at Borisov through a backyard telescope during its closest approach, you would have seen nothing unusual, just a fuzzy smudge with a faint tail, indistinguishable from any one of hundreds of comets that have graced our skies over the centuries. It looked like one of ours. But the spectrum told a very different story. When astronomers broke Borisov's light into its component wavelengths, they found molecular signatures that were both familiar and deeply strange. The familiar: water vapor, hydrogen cyanide, cyanide radical, diatomic carbon. These are molecules commonly found in the outgassing of solar system comets, and their presence in Borisov's coma was expected and comforting. It confirmed that Borisov was, at a basic level, made of the same kinds of stuff as our local comets. Ices and volatiles formed from the universal building blocks of interstellar chemistry. But one molecule stood out above all others in quantities that defied everything scientists thought they knew about cometary chemistry: carbon monoxide. Borisov was releasing carbon monoxide at an extraordinary rate, roughly 3 to 9 times more, relative to water, than any solar system comet ever measured at a comparable distance from the Sun. This was not a subtle anomaly. This was not a marginal excess that might be explained by measurement uncertainty or observational bias. This was a dramatic, unmistakable chemical signal that set Borisov apart from every single entry in the entire catalogue of known comets. The measurements were led by multiple independent teams using different telescopes and different techniques, and they all converged on the same conclusion. A team led by Dennis Bodowitz at Auburn University used the Hubble Space Telescope's Cosmic Origins spectrograph to detect carbon monoxide emission lines in the ultraviolet. A team led by Martin Cordiner at NASA's Goddard Space Flight Center used the Atacama Large Millimeter Array, ALMA, a vast network of 66 radio dishes spread across the high Atacama Plateau in Chile, to detect carbon monoxide at millimeter wavelengths with exquisite sensitivity and spatial resolution. Both teams found the same thing. Carbon monoxide was not just present in Borisov's outgassing, it was dominant. In the regions of the coma that ALMA could resolve, carbon monoxide appeared to be more abundant than water, a result that had no precedent in the study of any solar system comet. The carbon monoxide excess was the first sign that Borisov carried a chemical story fundamentally different from anything we had encountered before. It was the first crack in the assumption that comets, wherever they formed, would look roughly like ours. And it was the beginning of a scientific investigation that would push the boundaries of what we thought we understood about the formation and evolution of planetary systems across the galaxy. Here is the central mystery that Borisov forced the scientific community to confront. If objects like this exist, frozen remnants of alien planetary systems drifting silently through interstellar space, then where exactly did this one come from? What does its chemistry tell us about its birthplace? And how many more are out there that we have never seen? Begin with the first question. Where did Borisov originate? When astronomers traced the comet's trajectory backward in time, rewinding its path through the solar system, then outward through the surrounding interstellar medium, they found that it had arrived from the general direction of the constellation Cassiopeia. More precisely, its incoming velocity vector pointed back toward a region of sky near the binary star system Kruger 60, located roughly 13 light-years from Earth. 13 light-years is close by galactic standards. Kruger 60 is one of our stellar neighbors, but it is still a staggering distance in human terms. Light itself, traveling at nearly 300,000 kilometers per second, takes 13 years to traverse that gulf. Borisov, moving at 32 kilometers per second, roughly 1/10,000th the speed of light, would have needed far, far longer. Even at that velocity, which is fast enough to circle the Earth in about 20 minutes, the journey from Kruger 60 to our solar system would have taken approximately 350,000 years. But here is the problem. Stating that Borisov came from the direction of Kruger 60 is not the same as stating that it came from Kruger 60. Over hundreds of thousands of years, stars move. They orbit the galactic center at different speeds and along different paths, constantly shifting their positions relative to one another. A star that sits 13 light-years away from us today occupied a very different position 350,000 years ago. Tracing Borisov's trajectory backward far enough to pin down its exact parent star requires knowing the precise three-dimensional motions of every candidate star over enormous timescales, and those motions carry significant uncertainties. Several research teams attempted this forensic work. A 2020 study used data from the European Space Agency's Gaia spacecraft, the most precise star mapping mission ever flown, which has measured the positions, distances, and velocities of nearly 2 billion stars with unprecedented accuracy, to search for stars whose past trajectories might have intersected Borisov's incoming path. The approach was conceptually straightforward, but technically demanding. You take the current position and velocity of Borisov, calculate its trajectory backward through time, and then compare that path to the backward calculated trajectories of millions of nearby stars. If any star's past position lines up with the comet's incoming direction at the right time, that star becomes a candidate parent. The results were tantalizing, but ultimately inconclusive. A handful of candidate stars were identified, including Ross 128, a small red dwarf about 11 light-years away, and several other nearby systems. But no single star could be definitively linked to the comet. The uncertainties in both the stellar motions and Borisov's trajectory, compounded over hundreds of thousands of years, were simply too large. The error bars overlapped too much. The candidates were plausible but not confirmed. Borisov's birthplace, the star, the system, the disk of gas and dust where it first condensed into a solid body, remains unknown, and it may remain unknown forever, unless future astrometric missions achieve the extraordinary precision needed to trace interstellar trajectories over such vast timescales. Borisov's birthplace remains unknown. It is a letter written in an alien chemical language, delivered to our doorstep by interstellar currents, with no return address. We know the handwriting. We can read parts of the message, but we do not know who wrote it, or when or where they lived. And there is a poignant irony embedded in this anonymity. Borisov travelled for hundreds of thousands of years through the cold dark of interstellar space, carrying a chemical record of its birthplace, preserved in ancient ice, only to arrive in the one place in the galaxy where beings existed who could read that record, and then those beings could not trace it back to its source. The message arrived, the translation began, but the sender's address was illegible, and this anonymity matters enormously. Borisov's chemical composition, the unusual abundance of carbon monoxide, the specific ratios of hydrogen cyanide and water and diatomic carbon, is a direct record of the physical conditions in the environment where the comet formed. Temperature, pressure, radiation, the chemical makeup of the protoplanetary disk. All of these are encoded in the ice. If we could identify the parent star, we could cross-reference Borisov's chemistry with what we know about that star's planetary system. We could look for a protoplanetary disk, or for planets, or for other comets, and ask whether the chemistry matches. Without the parent star, we are interpreting a message without knowing the sender, the language, or the context. But here is what makes this truly terrifying. The problem is not just that we cannot identify where Borisov was born. The problem is what its mere existence tells us about the sheer number of objects like it that must be drifting through the galaxy at this very moment. Consider the math. Our solar system is small, vanishingly, absurdly small compared to the distances between stars. The Sun occupies a region of space so tiny, relative to the interstellar void, that the chance of a random object passing close enough for us to detect it is almost negligibly low. Imagine a single grain of sand falling randomly somewhere in the Pacific Ocean, and then imagine trying to spot that grain with a magnifying glass while standing on a single rock. The probability of success is essentially zero. And yet, between 2017 and 2019, a span of just 2 years, 2 interstellar objects passed through our inner solar system and were detected. 2 detections in 2 years does not mean the cosmos politely sent us 2 samples. It means these objects are everywhere. The detection of even a single interstellar visitor implies that the space between stars is populated with an almost unimaginable number of small, icy, rocky bodies, all drifting silently through the galaxy on trajectories that carry them from star to star over millions and millions of years. The numbers are striking. Based on the detections of Oumuamua and Borisov, and on the known sensitivity and sky coverage of the surveys that found them, researchers estimated the spatial density of interstellar objects in the solar neighborhood. The results were staggering. Some calculations suggested a density of roughly 1 interstellar object per cubic astronomical unit of space. 1 cubic astronomical unit is a volume approximately 93 million miles on each side, and within every such cube of space, on average, at least 1 silent wanderer drifts unseen. Scale that up. The volume of the Milky Way galaxy is colossal, a disk roughly 100,000 light-years across and 1 to 2,000 light-years thick, with a central bulge considerably thicker. Multiply the local density estimate across even a fraction of that volume, and the total number of interstellar objects in our galaxy becomes a number that defies easy comprehension. Some studies have estimated that the Milky Way contains on the order of 1 quadrillion, that is 1 followed by 15 zeros, interstellar objects larger than 100 meters in diameter. To visualize a quadrillion objects, consider this. If you could line them up side by side, each one the size of a football field, the line would stretch farther than the distance from Earth to the nearest star, and back again, many times over. Others, including theoretical work published by Amir Siraj and Avi Loeb at Harvard, have pushed the estimates even higher, suggesting numbers in the range of 10 to the power of 26, for objects down to a few meters in size. That is 100 trillion wandering fragments, invisible, undetected, unnoticed, filling the galaxy's interstellar spaces like dust motes in a cathedral. And these are not just abstract estimates. They carry testable predictions. If the density of interstellar objects is as high as these calculations suggest, then the upcoming Vera C. Rubin Observatory, a revolutionary survey telescope under construction in Chile, with a camera containing 3.2 billion pixels and the ability to photograph the entire visible sky every 3 nights, should detect several interstellar objects per year when it begins operations. Each detection would add another data point to our growing catalogue, another chemical fingerprint from another star system, another message in a bottle from the galactic ocean. Let that sink in. We live in a galaxy that is saturated with the shattered remnants of other worlds, fragments of planetary systems that formed, evolved, ejected their debris, and perhaps died, their leftovers now adrift in the dark, carrying chemical records of their origins, like messages in bottles thrown into an ocean of stars. And until 2017, we had never identified a single one. The implications cascade outward in every direction. If interstellar objects are this abundant, then the process that creates them, the ejection of icy, rocky material from young planetary systems, must be extremely common. It must happen around most stars, probably during the violent, chaotic early stages of planet formation, when giant planets are still migrating through their systems and scattering smaller bodies in every direction. We know this happened in our own solar system. Jupiter, in its youth, was not the stable, stately gas giant it appears today. Computer simulations of the early solar system, particularly the NICE model, developed in the early 2000s by a team of researchers including Alessandro Morbidelli, Harold Leveson, Cleomenes Tiganis, and Rodney Gomes at the NICE Observatory in France, suggest that Jupiter, Saturn, Uranus, and Neptune underwent a dramatic period of orbital migration during the first several 100 million years after the solar system formed. In this model, the giant planets formed in a more compact configuration than they occupy today, and their subsequent gravitational interactions with each other and with a surrounding disk of leftover planetesimals caused them to migrate. Jupiter moved slightly inward. Saturn, Uranus, and Neptune moved outward. In some versions of the model, Uranus and Neptune even switched their orbital positions during this violent reshuffling. The consequences of this migration were catastrophic for the smaller bodies in the solar system. Neptune, ploughing outward through the primordial disk, scattered billions of icy planetesimals in all directions. Some were thrown inward, where they briefly became comets before being absorbed by the Sun or ejected by further encounters with the giant planets. Some were hurled into the far reaches of the solar system, populating the Oort cloud, and some, perhaps as many as 90% of the original population, were flung out of the solar system entirely, launched on hyperbolic trajectories that carried them into interstellar space. Our solar system, during this epoch, was a fountain of icy debris, spraying fragments of its outer disk into the galaxy at velocities high enough to escape the Sun's gravity forever. Every star in the Milky Way that formed giant planets likely underwent a similar process, and we now know, thanks largely to the Kepler Space Telescope's revolutionary exoplanet survey, that planets are ubiquitous. Kepler discovered more than 2,600 confirmed exoplanets when its mission ended in 2018, and the data suggested that there are, on average, more planets than stars in the Milky Way. Giant planets, the gravitational bullies capable of ejecting material from a system, are present around a significant fraction of all stars surveyed. The raw material for producing interstellar objects exists everywhere, so the galaxy has been manufacturing these wanderers for billions of years. Star after star, system after system, ejecting its construction debris into the void. The interstellar medium is not empty. It is a highway, crowded with trillions of frozen fragments from trillions of planetary building sites, all drifting on timescales that dwarf human comprehension. If you could somehow see all of them at once, illuminate them, make them glow, the space between stars would not look empty at all. It would shimmer with an uncountable swarm of tiny, ancient, frozen bodies, each one carrying a chemical autobiography of a world we will never visit. Consider the implications for a moment from the other direction. If the Milky Way contains something approaching a quadrillion interstellar objects larger than 100 meters, then the total mass locked up in these wanderers is enormous. Estimates vary, but some calculations suggest a total mass equivalent to several times the mass of all the planets in our solar system combined. Others put it even higher. This is not negligible. This is a significant reservoir of material: water ice, carbon compounds, silicate minerals, complex organic molecules, dispersed across the galaxy, invisible to our telescopes, awaiting discovery by future instruments sensitive enough to detect them. And there is a deeper implication that most people miss. These objects do not merely drift passively through space. They interact gravitationally with every star they pass. Most interactions are negligible. The gravitational tug of a small icy body is vanishingly faint, but over billions of years, some fraction of these interstellar wanderers will be captured by the gravitational influence of a star they happen to pass close to, gently deflected onto bound orbits, and incorporated into a new solar system. In other words, some of the comets currently residing in our own Oort cloud, comets we have always assumed were born here, might actually be interlopers. Alien objects captured by the sun's gravity long ago, masquerading as locals. We would have no way to tell them apart from native comets without detailed chemical analysis. This idea, once considered fringe, has gained traction in recent years. Several theoretical studies have shown that the Sun, during its birth inside a dense stellar cluster roughly 4.6 billion years ago, could have gravitationally captured significant numbers of icy bodies from neighboring stars, as those stars and their disks were forming simultaneously in close proximity. The young Sun was not alone. It was born in a stellar nursery, surrounded by dozens or hundreds of sibling stars, many of which had their own protoplanetary disks shedding material into the shared environment. In that dense, chaotic setting, the exchange of cometary material between forming systems would have been almost inevitable. If this is true, then some of the objects we see in the outer Oort cloud might carry chemical signatures that do not quite match the rest of our solar system's comets. They might be detectably different, if only we had the tools and the opportunity to study them closely enough. Borisov, in this context, is not just a passing visitor. It is a preview. It shows us what captured alien comets might look like if we could somehow reach them. Borisov is not an anomaly. Borisov is normal. What was anomalous was that, after 4.5 billion years, we finally had the technology to catch one in the act of passing through. But the mystery deepens considerably when you examine what Borisov was actually made of. Remember the carbon monoxide. When astronomers split Borisov's light into a spectrum and identified the molecules in its outgassing, they found water, they found hydrogen cyanide, they found diatomic carbon and cyanide radical, all molecules commonly seen in solar system comets. But one molecule dominated the chemical profile in a way that had never been seen before. Carbon monoxide. Borisov was releasing carbon monoxide at a rate that was extraordinary, roughly 3 to 9 times higher, relative to water, than any solar system comet ever measured at a comparable distance from the Sun. This was not a subtle difference. This was not a marginal outlier. This was a dramatic, unambiguous chemical anomaly that set Borisov apart from every comet in our catalogue. And the carbon monoxide abundance was not just an interesting data point. It was a key that unlocked information about where and how the comet had formed. To understand why, we need to briefly consider how cometary ice works. A comet is not a uniform block of frozen material, like an ice cube from a freezer. It is a complex mixture of different ices: water ice, carbon dioxide ice, carbon monoxide ice, methane ice, ammonia ice, and others, all blended together with grains of silicate rock and organic dust in a loosely packed, porous structure. The relative proportions of these different ices are determined by the temperature and pressure conditions that existed in the region of the protoplanetary disk where the comet formed. Each molecule has a specific condensation temperature, the temperature below which it transitions from gas to solid. Water condenses at around negative 170 degrees Celsius. Carbon dioxide at around negative 195 degrees Celsius. And carbon monoxide at around negative 210 degrees Celsius. just 63 degrees above absolute zero, the theoretical minimum temperature where all molecular motion ceases. This hierarchy of condensation temperatures creates what planetary scientists call snowlines, concentric boundaries in a protoplanetary disk where different volatile species transition from gas to ice. Close to the star, where temperatures are high, only the most refractory materials, rocks and metals, can exist as solids. Farther out, you cross the water snow line and water ice can form. Farther still, you cross the carbon dioxide snow line, and in the most distant, coldest regions of the disk, you finally cross the carbon monoxide snow line, where this hypervolatile compound can freeze and be incorporated into solid bodies. The abundance of carbon monoxide in a comet, therefore, is a thermometer. It tells you how cold the birthplace was. A comet with lots of carbon monoxide formed beyond the carbon monoxide snow line, in a region of extreme cold. A comet with little or no carbon monoxide formed closer in, where temperatures were too high for this volatile molecule to survive in solid form. Solar system comets contain carbon monoxide, but typically in modest amounts relative to water. The ratios vary, but they generally fall within a well-characterized range that is consistent with formation in the outer solar system. Cold, but not the coldest possible environment. Borisov shattered that range entirely. Its carbon monoxide to water ratio was 3 to 9 times higher than any solar system comet measured at a comparable distance from the Sun. Whatever environment produced Borisov was colder, more extreme, and more chemically unusual than the birthplace of any known local comet. One hypothesis was that Borisov formed in the outermost regions of its parent star's protoplanetary disk, the vast, cold ring of gas and dust that surrounds every young star during the early stages of planet formation. Every protoplanetary disk has a temperature gradient, hot near the star, cold farther out. The exact temperature profile depends on the luminosity of the central star, the density of the disk, and the amount of heating from various processes. In our own solar system, the equivalent of the extremely cold outer zone would be far beyond Neptune, perhaps beyond the classical Kuiper belt entirely, in the deep freeze zone where temperatures plummet to just 10 or 20 degrees above absolute zero. Comets that condense in these frigid regions would naturally be saturated with hypervolatile compounds, because those compounds can freeze out of the gas phase only at such extreme temperatures. A lower mass star, a red dwarf for example, which produces far less light and heat than our Sun, would have its carbon monoxide snowline located much closer in, and comets forming at relatively modest distances from such a star could still accumulate the hypervolatile-rich chemistry that we observed in Borisov. This was the leading hypothesis, and it was supported by modelling work published by several research groups. Planetary scientists at the Leiden Observatory in the Netherlands ran chemical evolution models of protoplanetary disks with varying stellar masses and luminosities, and showed that carbon monoxide to water ratios comparable to Borisov's could be produced in the outer regions of disks, stars somewhat less luminous than the Sun. The physics was sound, the numbers worked, but there was no way to confirm which specific type of star had produced Borisov, because the parent star remained stubbornly unidentified. But there was a second, more provocative possibility. What if Borisov did not form around a star at all? What if it condensed directly from the cold molecular cloud, the vast, dense cloud of interstellar gas and dust that exists before star formation even begins? Molecular clouds are among the coldest natural environments in the known universe. They are vast structures, spanning dozens of light years, containing enough mass to form hundreds or thousands of new stars. Their dense interiors can reach temperatures of just 10 degrees above absolute zero, colder than the surface of Pluto, colder than the Oort cloud, colder than virtually any other environment in the galaxy, except the cosmic microwave background itself. Material that condenses inside these clouds before any protostar has ignited to warm its surroundings would be saturated with carbon monoxide and other hypervolatile species that can freeze at these extreme temperatures. If Borisov formed inside such a molecular cloud, perhaps condensing as a small icy body before being incorporated into a collapsing protostellar core and later ejected from the resulting planetary system, its extraordinary carbon monoxide content would make perfect physical sense. It would be a relic not just of another planetary system, but of the interstellar medium itself, a piece of the raw material from which stars and planets are built, preserved in solid form for billions of years. This idea was speculative. It required a chain of events: condensation in a molecular cloud, incorporation into a collapsing protostellar core and its forming planetary system, gravitational ejection from that system by a massive planet, and then a journey of millions of years through the galaxy before arriving in our solar system. That, while physically plausible at each individual step, was difficult to confirm or refute with the data available from a single comet observed over a few months. Most researchers in the field favored the more conventional explanation: formation in the cold outer reaches of an otherwise normal protoplanetary disk, followed by gravitational ejection from the system by a massive planet. But the molecular cloud hypothesis could not be definitively ruled out, and the mere fact that it was seriously considered by multiple research groups illustrated just how much we did not, and still do not, understand about the origins, histories, and chemical evolution of interstellar wanderers. And it gets worse. In late March of 2020, just a few months after Borisov had passed its closest point to the Sun, something unexpected happened. Astronomers using the Hubble Space Telescope detected changes in the appearance of the comet's nucleus. The normally round, compact central brightness had elongated. Subsequent observations confirmed the news. The nucleus had fragmented. At least one significant piece had broken away from the main body, and both pieces were actively outgassing, surrounded by their own individual clouds of dust and vapor. Cometary fragmentation is not unknown in our solar system. Comet Shoemaker-Levy 9 famously broke into more than 20 pieces before slamming into Jupiter's atmosphere in 1994, creating dark impact scars larger than the Earth. Comet Linear disintegrated entirely during its close approach to the Sun in 2000. Splitting and crumbling is part of the life cycle of comets. Their icy structures are fragile, riddled with voids and fractures, held together more by chance than by structural integrity. But Borisov's fragmentation was scientifically significant for a specific reason. When a cometary nucleus breaks apart, it exposes fresh ice from the interior, material that has been shielded from sunlight, cosmic rays, and surface processing since the comet first formed. This freshly exposed ice begins to sublime immediately, and the chemical signatures it produces are among the purest windows into the comet's original composition. It is as though the comet, in crumbling, is revealing the chemistry of its innermost core, ice that may not have seen light or felt warmth since it first condensed from a cloud of gas around an alien star in a time and place we cannot identify. The Hubble Space Telescope tracked the fragmentation event over several weeks. Images showed the detached piece fading rapidly, consistent with a small chunk of exposed ice sublimating away into nothing. The main body, meanwhile, continued to brighten as it approached the Sun, indicating that it retained sufficient mass to sustain vigorous outgassing. The fact that Borisov had split at all was itself informative. It suggested a loosely consolidated structure, riddled with internal voids and fracture planes, a body held together more by weak cohesive forces than by gravitational binding. This is consistent with what we know about many solar system comets. When Comet Shoemaker-Levy 9 was torn apart by Jupiter's tidal forces in 1992, 2 years before the fragments impacted the planet, the ease with which it disintegrated revealed that comets are remarkably fragile objects, more like compacted snowdrifts than solid rock. And what the fresh interior ice from Borisov's breakup revealed was entirely consistent with what the surface had already been telling us. Carbon monoxide remained the dominant volatile. The interior was as rich in this hypervolatile compound as the outer layers. This was not a surface veneer. This was not a thin coating of unusual chemistry over a more ordinary core. The carbon monoxide abundance was the fundamental makeup of the comet, uniform from surface to center. Borisov was, through and through, a deeply alien object disguised in the familiar shape of a comet. The fragmentation also sharpened estimates of the nucleus size. Before the breakup, the best estimate placed the nucleus at roughly 1 kilometer in diameter, perhaps slightly smaller, comparable in scale to a large hill or a small mountain. After the split, The surviving main fragment appeared to be approximately 500 meters across, roughly the length of 5 football fields placed end to end. This is small by cometary standards. Comet Hale-Bopp's nucleus is estimated at approximately 40 kilometers across, so large that if you stood on one side, you would not be able to see the other side, even on a clear day. Even Churyumov-Gerasimenko, visited by the Rosetta mission, has a nucleus about 4 kilometers wide. Borisov was tiny, a modest, fragile snowball from another star, slowly falling apart under the sun's warmth during what was probably its first and only close encounter with a star since it left its birthplace. But here is the question that haunted researchers and continues to challenge our interpretation of every measurement we made. How much of Borisov's original mass and chemical inventory had already been lost before it ever reached us? The interstellar medium is often described as a vacuum, and by everyday standards it is. But it is not truly empty. It contains, on average, about 1 atom per cubic centimeter, mostly hydrogen. It is also pervaded by cosmic rays, high-energy protons, and heavier atomic nuclei that have been accelerated to velocities approaching the speed of light by the shock waves of distant supernova explosions. These particles permeate the galaxy, and they bombard everything in their path. When a cosmic ray strikes the surface of an icy body like Borisov, it penetrates centimeters or even meters into the ice, breaking molecular bonds, creating new chemical species through radiation chemistry, and slowly sputtering away surface material atom by atom. Over millions of years, this relentless, invisible bombardment can erode the outermost layers of a small body by a significant amount, perhaps meters, perhaps tens of meters of surface material stripped away over geological timescales. In addition, ultraviolet radiation from the combined starlight of billions of distant suns, faint but omnipresent in interstellar space, gradually photodissociates molecules on exposed ice surfaces. And even in the deepest cold of the void, where temperatures hover just a few degrees above absolute zero, the most volatile compounds can sublime at vanishingly small but non-zero rates. Over timescales of millions of years, even an infinitesimal rate of sublimation adds up. Borisov had been traveling through this environment for at least hundreds of thousands of years, and possibly for millions or even tens of millions of years, depending on its ejection velocity and the distance to its parent system, which we cannot determine. By the time it arrived in our solar system, it was almost certainly a diminished, weathered version of whatever it had originally been when first ejected from its birthplace. A worn remnant, a faded manuscript. The question scientists grappled with was uncomfortable in its implications. How much of the original text was still legible? How faithfully did the chemistry we so carefully measured represent the conditions of Borisov's birthplace versus the cumulative effects of its long interstellar journey? Something is wrong with our assumptions. For decades, cometary scientists had treated the chemical composition of a comet as a relatively direct readout of the conditions under which it formed. Measure the ice, and you can deduce the temperature, pressure, and chemical environment of the comet's birthplace. It was a clean, elegant framework, but Borisov introduced a disquieting complication. If the journey itself, the millions of years of cosmic ray bombardment and slow sublimation in the interstellar void, could significantly alter a comet's chemistry, then the message encoded in the ice might be corrupted by the medium through which it traveled. We might be reading not the birthplace, but the journey, or some indeterminate blend of both. And there was one more unsettling wrinkle. When astronomers analyzed the dust streaming off Borisov, not the gas, but the solid particles carried outward by the sublimating ice, they found something unexpected. The dust grains appeared to be unusually compact, rich in carbon-bearing compounds, and smaller on average than the dust from most solar system comets. Polarimetric observations, which measure how light scatters off the dust at different angles, supported this picture. Borisov's dust was most similar in its optical properties to the dust found in one very specific solar system comet, Comet Hale-Bopp, which is itself unusual among local comets for its high dust-to-gas ratio and its origin in the outer reaches of the solar system. But here was the contradiction. The carbon-rich, compact dust suggested formation conditions that were relatively warm, consistent with the inner regions of a protoplanetary disk, where temperatures are higher and organic molecules are baked into denser, more refractory structures. Yet the hypervolatile ice pointed to the outermost, coldest regions. Borisov seemed to carry a contradictory record: warm dust from closer in, cold ice from the deep freeze. It was as though the comet had been assembled from ingredients sourced from vastly different parts of its parent system. One explanation was radial mixing, the process by which turbulent flows within a protoplanetary disk transport material from the hot inner regions to the cold outer regions, and vice versa. This is known to occur. NASA's Stardust mission, which collected dust samples from Comet Wild 2 and returned them to Earth in 2006, found mineral grains called calcium-aluminum-rich inclusions that could only have formed at extremely high temperatures, full day, very close to young sun, yet they were embedded in icy material from the cold outer solar system. The disk had shuffled its ingredients before the planets finished forming. If Borisov's parent system experienced similar mixing, it would explain the contradictory signatures. And if that mixing was similar in character to what happened in our own solar system, it would suggest that the fundamental processes of planet formation, the turbulence, the gravitational stirring, the radial transport of material across vast distances within a protoplanetary disk, are not unique to our corner of the galaxy. They are common, perhaps universal, the same cosmic recipe, executed with local variations in temperature and composition and stellar environment, in star system after star system across the galaxy. The universe, it appears, does not invent new physics for every new planetary system. It uses the same toolkit, the same chemical building blocks, the same physical processes, and produces comets that are recognizably similar, yet measurably different, like regional dialects of the same language. This revelation, emerging from a single small comet passing through our solar system over the course of a few months, is staggering in its implications. It suggests that a sufficiently large sample of interstellar objects, dozens, hundreds, eventually thousands, could allow us to build a statistical picture of planet formation across the entire galaxy. We could measure the range of chemical compositions, the distribution of carbon monoxide abundances, the variety of dust properties, and from these measurements, we could infer the diversity of formation environments. We could answer questions that have been theoretical for decades. Are most protoplanetary disks chemically similar to ours? Do most planetary systems form comets? Do the comets that form around different types of stars, red dwarfs, sun-like yellow stars, massive blue giants, differ systematically in their chemistry? One interstellar comet cannot answer these questions, but it proves that the method works. It proves that the galaxy is delivering samples to our doorstep, and that we can read them if we are paying attention. This is the core problem that Borisov laid bare, and it is far larger than a single comet. We are not simply studying one interesting visitor, we are attempting forensic science on an interstellar scale, trying to reconstruct the birth environment of an unknown planetary system from a single, small, fragmentary, and partially corrupted piece of evidence that drifted to us across light years of empty space. It is like trying to deduce the layout of a house from a single brick that was mailed to you from an unknown address, with some of the mortar scraped off in transit. And yet, despite these enormous limitations, Borisov told us something we could not have learned any other way. It told us that at least one other planetary system, somewhere in our galactic neighborhood, formed comets that are recognizably similar to our own, and also measurably different. Similar enough to have a coma and a tail. Different enough to carry chemical fingerprints that match no local comet in our catalogue. The universe, it seems, builds planetary systems using the same fundamental ingredients but in different proportions. The recipe is universal, the seasoning is local, and if that is true, then every interstellar object that passes through our solar system is a sample from a different kitchen, a frozen message from a distant birthplace, carrying clues about temperatures, pressures, chemistry, and history that we could never access any other way. Each one is a probe, sent not by intelligence, but by the blind mechanics of gravity and orbital dynamics, arriving at our doorstep after journeys of unimaginable duration through the silent, frozen emptiness between the stars. We found 2 in 2 years. How many are we missing? How many passed through the inner solar system last year, or last century, or during the entire span of human civilization, without anyone ever knowing? And what messages are they carrying? Chemical testimonies from worlds we will never visit, frozen records of star systems that may have died before our sun was born. The answer is out there, locked in ice, drifting through the dark. We just need to learn how to read it. The discovery of Borisov did not just raise questions. It launched a series of ambitious scientific investigations, each one a separate chapter in the global effort to understand what this object was, where it came from, and what it meant for our understanding of the galaxy. Over the months and years that followed, multiple independent research teams tackled the problem from different angles, using different instruments, different analytical techniques, and different theoretical frameworks. Each investigation hoped to crack a different piece of the puzzle. Each one uncovered something unexpected, and each one, in its own way, deepened the mystery rather than resolving it. The first and most urgent investigation was the spectroscopic campaign, the effort to decode Borisov's chemical fingerprint in real time as it approached the Sun. This campaign began almost immediately after the interstellar classification was confirmed. The logic was straightforward. As Borisov drew closer to the Sun, its surface would warm, and the increasing heat would cause different volatile compounds to sublime at different rates, depending on their individual sublimation temperatures. By tracking which molecules appeared in the coma at which distances from the Sun, scientists could build a layered picture of the comet's composition, a kind of thermal peeling where each increase in temperature exposed a new chemical layer. The first molecule detected was cyanide radical, identified in spectra taken by the William Herschel telescope in September of 2019, when Borisov was still roughly 3 astronomical units from the Sun, about 3 times the Earth-Sun distance. Cyanide radical is a common molecule in cometary Comet, produced by the photodissociation of hydrogen cyanide under ultraviolet sunlight. Its detection was expected and unremarkable. It placed Borisov squarely within the normal range of cometary behavior. Then came the detection of diatomic carbon, another standard cometary molecule, seen in spectra from the Gemini North Telescope and several other facilities. The abundance of diatomic carbon relative to cyanide was measured, and the ratio fell within the range observed for solar system comets. Specifically, it was consistent with the so-called typical comets rather than the carbon chain depleted class that includes some Jupiter family comets. This was mildly interesting but not alarming. Borisov, chemically, was behaving like a well-behaved visitor. Researchers breathed a cautious sigh of relief. The first interstellar object, Oumuamua, had been frustratingly uncooperative, too small, too faint, and too devoid of outgassing to permit any chemical analysis at all. Borisov, by contrast, was obligingly active, dutifully sublimating, and producing a coma rich enough in molecules to yield clean spectral detections. It was, in the jargon of observational astronomers, a cooperative target. The standard molecules were showing up on schedule, at the expected abundances, following the expected patterns. The alien comet was reading from a familiar script. But then the carbon monoxide detections arrived and everything shifted. In late November and December of 2019, as Borisov neared its closest approach to the Sun, a distance of roughly 2 astronomical units, placing it in the vicinity of Mars's orbit, 2 independent teams announced the detection of carbon monoxide in quantities that were unprecedented for any comet observed at that solar distance. The first team, led by Denis Bodowitz at Auburn University, used the Hubble Space Telescope's Cosmic Origins spectrograph to observe Borisov in the ultraviolet. They detected emission from carbon monoxide ions, electrically charged carbon monoxide molecules that had been ionized by solar ultraviolet radiation, and from the derived production rates, they estimated that Borisov was releasing carbon monoxide at a prodigious rate. The results were published in Nature Astronomy in the spring of 2020, and the numbers were startling. Carbon monoxide was being produced at roughly the same rate as water, or possibly even faster, in solar system comets observed at similar distances from the Sun. carbon monoxide production is typically a small fraction of the water production rate. In Borisov, it was comparable to or exceeding it. The second team, led by Martin Cordiner at NASA's Goddard Space Flight Center, used ALMA, the Atacama Large Millimeter/Submillimeter Array, to observe Borisov at radio wavelengths. ALMA is arguably the most sensitive millimeter-wave telescope ever built, consisting of 66 individual radio dishes spread across the Atacama Plateau at an altitude of 5,000 meters, working together as a single enormous interferometer. Cordiner's team detected the rotational emission lines of carbon monoxide and hydrogen cyanide directly, and their measurements confirmed and extended Bodewicz's results. The carbon monoxide abundance was extraordinary. It was not just higher than expected, it was off the charts. No solar system comet, observed under comparable conditions, had ever shown anything like it. As Cordiner himself later noted, the result was so extreme that the team initially questioned their own data. They reprocessed the observations. They checked the calibration. They verified the spectral line identification. Everything held. The carbon monoxide was real, it was abundant, and it demanded explanation. The math is striking. At 2 astronomical units from the Sun, a typical solar system comet might produce carbon monoxide at a rate of roughly 10 to the 25th molecules per second, a large number in absolute terms, but modest relative to water production. Borisov, at the same distance, was producing carbon monoxide at rates several times higher, with some estimates placing the carbon monoxide to water production rate ratio at values approaching or even exceeding unity. This single measurement, more than any other, marked Borisov as chemically alien. To appreciate just how extraordinary this measurement was, you need to understand the context of cometary volatile surveys. Over the preceding decades, astronomers had built a substantial database of volatile compositions for solar system comets. Missions like Rosetta, which orbited Comet 67P/Churyumov-Gerasimenko for more than 2 years, had provided exquisitely detailed inventories of the gases boiling off a comet's surface. Ground-based surveys using infrared telescopes had measured the volatile compositions of dozens of comets as they passed through the inner solar system, and from all of this data, a general picture had emerged. Solar system comets, while individually variable, all fell within a recognizable family of compositions. Water-dominated. Carbon monoxide, when present, was typically a minor constituent, present at levels of a few percent relative to water, occasionally reaching 10 or 15% in particularly carbon monoxide-rich comets, but never approaching parity. Borisov shattered that pattern. Its carbon monoxide to water ratio was not just high, it was not just unusual, it was in a completely different regime, a regime that no solar system comet had ever occupied. It was as if someone had been cataloguing the heights of human beings for decades, measuring thousands of individuals, building a careful statistical distribution, and then one day encountered a person who was 12 meters tall, not unusual, not an outlier, a fundamentally different category. And the detection came from 2 independent teams, using 2 entirely different methods: ultraviolet spectroscopy from orbit and millimeter wave interferometry from the ground, which made it essentially impossible to dismiss as an instrumental artifact. When 2 independent techniques produce the same anomalous result, the anomaly is almost certainly real. The scientific community accepted it rapidly. Within months of the initial publications, the extreme carbon monoxide enrichment of Borisov had become one of the established facts of interstellar object science. But the questions it raised were profound and unsettling. Why was there so much carbon monoxide? Where had it come from? What kind of environment could produce a comet so radically enriched in a molecule that, in our own solar system, is typically a minor player? And perhaps most importantly, was Borisov's chemistry representative of comets in its parent system, or was it itself an outlier, a freak even among its siblings? These questions could not be answered by observation alone. They required theory. But before theory could be applied, the spectroscopic campaign itself needed to be pushed further. Other molecules remained to be detected, and the observing window was narrowing with every passing week. As Borisov approached perihelion, its closest point to the Sun. Additional spectroscopic observations were conducted across a wider range of wavelengths. Teams using infrared spectrographs on the Keck Observatory and the Very Large Telescope searched for the signatures of other volatile species: methanol, formaldehyde, ethane, acetylene. These molecules, while less abundant than water and carbon monoxide, provide critical additional constraints on formation temperature and disk chemistry. The detection of methanol, for instance, would indicate the presence of ice that formed through grain surface chemistry at temperatures around 10 to 20 Kelvin, chemistry that occurs on the surfaces of tinier dust grains in the cold outer regions of protoplanetary disks, where atoms slowly hop from site to site on the grain surface and combine into increasingly complex molecules. Some of these species were tentatively detected, though at lower confidence than the robust carbon monoxide and cyanide radical detections. The difficulty was partly one of sensitivity. Borisov was faint, and the molecular emission lines of trace species were buried in the noise, and partly one of timing. Borisov's closest approach to the Sun occurred in early December of 2019, and after that the comet began to recede, its brightness fading as the distance to the Sun increased, and the outgassing rate declined. The observing window for detailed spectroscopy was roughly 3 to 4 months, from late October through early February, with the best conditions clustered around the few weeks nearest perihelion. After that, Borisov's signal grew too faint for high-resolution spectroscopy, and the chemical reconnaissance was essentially over. This time pressure was one of the defining features of the entire Borisov campaign. Unlike a solar system comet, which might return decades or centuries later for another observation, an interstellar visitor is a one-time opportunity. Miss it, and it is gone forever. Every observation had to be planned and executed with the knowledge that there would be no second chance. The telescopes had to be ready. The proposals had to be written. The observing time had to be allocated. And it all had to happen within a few weeks or months, on a schedule dictated not by funding agencies or review panels, but by the cold geometry of celestial mechanics. This urgency produced a remarkable spirit of collaboration across the astronomical community. Competing research groups shared data, coordinated observations to avoid duplication, and published results rapidly, sometimes within weeks of the observations, rather than the months or years typical of astronomical publication cycles. The Borisov campaign was, in many ways, a model of how science operates at its best, a global community mobilizing around a shared time-critical opportunity, pooling resources and expertise to extract every possible bit of information from a fleeting, unrepeatable event. But what did it mean? The answer depended on interpretation, and interpretation depended on models. Models of protoplanetary disk chemistry, models of cometary formation, models of interstellar processing. And this is where the second major investigation entered the picture: the theoretical modeling campaign that attempted to connect Borisov's observed chemistry to specific formation environments. Several research groups around the world launched modeling efforts in parallel. At the Leiden Observatory in the Netherlands, a team led by Christian Eystrup and Ewan van Dijk ran detailed chemical evolution models of protoplanetary disks with different properties, different stellar luminosities, different disk masses, different temperature profiles, different dust-to-gas ratios. Their goal was to determine what kind of disk environment could produce a comet with Borisov's specific chemical signature, high carbon monoxide, moderate hydrogen cyanide, and the particular dust properties observed by polarimetric campaigns. The models pointed toward formation in the outer regions of a disk around a star less luminous than our Sun, perhaps a K-type star or an M-type red dwarf. In such a disk, the carbon monoxide snowline, the distance from the star beyond which carbon monoxide can freeze into solid ice, would be located closer to the star than in our own solar system because the star produces less heat and light. Comets forming just beyond that snowline would be enriched in carbon monoxide relative to water because they would incorporate large amounts of freshly frozen carbon monoxide ice. The Leiden models showed that the observed ratios were consistent with this picture, particularly for disks around stars with luminosities between about 1/10 and 1/2 that of our Sun. This was an important result. It provided a plausible astrophysical context for Borisov's chemistry and suggested that the comet had not formed in an exotic or unprecedented environment. It had formed in a perfectly normal protoplanetary disk, just one with slightly different physical parameters than our own. The universe's diversity of stellar environments naturally produces a diversity of cometary chemistries. Borisov was not alien in the sense of being inexplicable. It was alien only in the sense of being different. A product of another kitchen using the same ingredients in different proportions. But the models also revealed something uncomfortable. The chemical composition of a comet is sensitive to many parameters: disk temperature, gas density, ultraviolet radiation field, the timescale of formation, the degree of radial mix, and the thermal history of the disk over millions of years. With so many free parameters, many different disk configurations could produce carbon monoxide to water ratios in the range observed for Borisov. The chemical fingerprint, in other words, was not unique. It did not point to one specific type of parent system. It was consistent with multiple possible origins. The message was legible, but the return address remained smudged. This ambiguity troubled researchers deeply. The whole promise of interstellar object science rested on the idea that chemical fingerprints could be decoded, that measuring the volatile composition of an alien comet could tell you something specific about where it formed and what its parent system was like. If the fingerprint was too degenerate, if too many different environments could produce the same result, then the entire enterprise lost much of its diagnostic power. You would be reading a message, but unable to identify the sender. Some theorists argued that additional constraints could break the degeneracy. If the dust properties, the isotopic ratios, and the volatile abundances could all be measured simultaneously, the combined dataset would narrow the range of possible parent systems much more effectively than any single measurement alone. Others pointed out that such comprehensive characterization was extremely difficult for a fast-moving interstellar visitor that would be observable for only a few months. Borisov offered a richer dataset than Oumuamua, certainly, but it was still far less than what a dedicated mission could obtain. Still others raised a more fundamental concern. Even with perfect chemical characterization, the mapping from chemistry to formation environment might never be unique. Protoplanetary disks are complex systems with internal dynamics. Turbulent mixing, radial transport of material, time-varying thermal structures that can blur the chemical signatures of specific formation locations. A comet that formed at 30 astronomical units in one disk might end up with the same volatile ratios as a comet that formed at 10 astronomical units in a different disk with different properties. The chemistry remembers some things and forgets others. It is an imperfect record, better than nothing, far better than nothing, but not the clean, one-to-one mapping that the most optimistic researchers had hoped for. This realization tempered the initial excitement, but did not extinguish it. Even imperfect information is valuable when you previously had none, and the theoretical modeling campaigns produced one result that was broadly accepted. Borisov almost certainly did not form in a solar system like ours. Whatever its parent system was, it was different. Different enough to produce a comet with a chemical makeup that falls completely outside the range seen in our own system's cometary population. The models disagreed about the details, but they agreed on this central point. The third investigation focused on something entirely different: the physical structure of Borisov's nucleus and what its properties could tell us about conditions in the alien system where it formed. This work was led primarily by teams using the Hubble Space Telescope and ground-based adaptive optics systems. The challenge was considerable. Borisov's nucleus was estimated at roughly 1 kilometer in diameter, possibly smaller, and at its closest, it was still roughly 300 million kilometers from Earth. At that distance, even Hubble could not directly resolve the nucleus. It appeared as an unresolved point of light buried within the much brighter coma of gas and dust surrounding it. To estimate the nucleus size, scientists had to use indirect methods, measuring the total brightness of the central condensation, subtracting the estimated contribution from the coma, and attributing the remaining light to sunlight reflected off the solid surface of the nucleus. The results placed the nucleus diameter at between 400 meters and 1 kilometer. This is small but not extraordinarily so. Solar system comets span an enormous range of sizes, from nuclei just a few hundred meters across, like the tiny comet observed during the Deep Impact mission, to behemoths like Comet Hale-Bopp at 40 kilometers or Comet Bernardinelli-Bernstein, discovered in 2021, with a nucleus estimated at around 137 kilometers in diameter, making it the largest comet ever identified. But the smallness of Borisov's nucleus had an important implication for the fragmentation event that followed. Small nuclei have less self-gravity holding them together. They are more vulnerable to thermal stresses. The differential expansion that occurs when one side of the nucleus is heated by the sun while the other side remains in shadow, and they are more susceptible to rotational disruption. The tendency for a spinning body to fly apart if its rotation rate exceeds the threshold where centrifugal force overwhelms the material's cohesive strength. Borisov's subsequent breakup was consistent with a body that was barely holding itself together, a loosely packed aggregate of ice and dust that succumbed to the stresses of its close solar encounter. The physical characterization also yielded insights into the internal structure of Borisov that were impossible to obtain for most solar system comets at comparable distances. Polarimetric observations, measurements of how the orientation of light waves changes when sunlight scatters off cometary dust particles, revealed that Borisov's dust had properties remarkably similar to a specific solar system comet, Hale-Bopp, the spectacular visitor that graced Earth's skies in 1997. The polarimetric similarity suggested that Borisov's dust grains were comparable in size, shape, and composition to those of Hale-Bopp, primarily submicron particles, rich in carbon and silicates, with a fluffy, aggregate structure rather than a compact, crystalline one. This comparison with Hale-Bopp was more than a casual resemblance. Hale-Bopp was itself an unusual comet, an extremely active, large nucleus visitor that produced an exceptionally dust-rich coma and showed evidence of having formed in the cold outer reaches of our own solar system's protoplanetary disk. The fact that Borisov's dust shared Hale-Bopp's polarimetric signature suggested that both comets formed under broadly similar physical conditions. Cold temperatures, low collision velocities, and the slow, gentle aggregation of submicron grains into larger porous structures. This was simultaneously expected and informative. Expected because the basic dust-forming processes in protoplanetary disks, the condensation of silicates and carbon compounds from the gas phase, the slow growth of grains through collisions and sticking, are governed by physics that should operate similarly in any disk. Informative because it confirmed that the dust-forming environment in Borisov's parent system produced material that was physically indistinguishable, at least in its optical scattering properties, from dust in our own system. The dust was universal, the ice was anomalous. This contrast, familiar solids embedded in alien ice, was one of the most striking features of Borisov's overall characterization. Additionally, thermal modeling of the nucleus provided constraints on its porosity. A highly porous body, essentially a loosely packed snowball with large internal voids, would respond differently to solar heating than a compact, dense one. The porosity affects how quickly heat penetrates the interior, how efficiently gas escapes through the subsurface, and how the nucleus deforms under the stress of uneven heating. The models suggested that Borisov's nucleus was indeed highly porous, with void fractions possibly exceeding 50 or 60%. This is consistent with what we know about solar system comets. The Rosetta mission found that Comet 67P has a porosity of about 70 to 80%, making it less dense than water and structurally more like a loosely packed snowdrift than a solid rock. Borisov, it seemed, shared this fragile, porous architecture. The implications were significant. If comets in our solar system and comets from other systems both independently evolve porous, fragile, aggregate structures, then this morphology may be a universal feature of cometary formation, a natural consequence of the gentle, low-velocity accretion processes that build cometary nuclei from smaller particles in the outer reaches of any protoplanetary disk. The physics that builds comets, like the physics that builds dust grains, appears to work the same way regardless of the star at the center of the system. The fourth investigation was perhaps the most creative and far-reaching, the attempt to determine whether Borisov had ever been close to a star before. This question matters because a comet that is making its first ever approach to a star will behave differently from one that has been heated before. A pristine, never-before-warmed comet will have all of its volatile ices intact, including the most easily sublimated species like carbon monoxide and molecular nitrogen. When it first encounters stellar heat, these hypervolatile compounds will blast off the surface in a spectacular burst of outgassing, producing an exceptionally active comet for its size. A comet that has previously been heated, on the other hand, will have already lost its most volatile surface layers during earlier encounters, and will appear relatively sedate when it returns. Borisov's extreme carbon monoxide outgassing was strongly suggestive of a comet experiencing stellar heating for the very first time. If it had passed close to another star in the past, its parent star, or any star it encountered during its interstellar journey, the intense carbon monoxide on its surface would have been driven off during that earlier encounter, leaving behind a more depleted, water-dominated composition. The fact that so much carbon monoxide remained and that it erupted so vigorously when the sun began to warm Borisov's surface suggested that this ice had been locked away in pristine, untouched cold since the comet's formation. Borisov, it appeared, was a virgin comet, one that had never felt the warmth of any star before our sun. This conclusion was supported by an analysis of the comet's thermal evolution during its interstellar journey. Researchers modeled how deeply the sun's heat would penetrate Borisov's nucleus during its passage through the inner solar system and compared this to how deeply interstellar cosmic rays would have processed the surface layers during its long voyage through the galaxy. The models suggested that the sun's heat was reaching ice layers that had never been warmed or processed by any prior stellar encounter, ice that had been in cold storage since the comet first formed, preserved at temperatures only marginally above absolute zero for hundreds of thousands or millions of years. The thermal modeling was remarkably detailed. The researchers treated the nucleus as a layered structure, with each layer characterized by its thermal conductivity, porosity, and volatile content. As Borisov approached the sun, the surface temperature rose and a thermal wave propagated inward, slowly, because ice and porous regolith are poor conductors of heat. At 2 astronomical units from the sun, the thermal wave had penetrated only a few meters into the surface. Deeper than that, the ice remained at its interstellar equilibrium temperature of roughly 10 to 15 Kelvin, warmer than the cosmic microwave background at just under 3 Kelvin because of the slow trickle of energy deposited by cosmic ray impacts, but vastly colder than the surface. The cosmic ray processing layer extended deeper, perhaps a meter or two into the surface for a comet that had been traveling through interstellar space for a few 100,000 years, or several meters for one that had been traveling for millions. But even this irradiated rind was thin compared to the total volume of the nucleus. Most of the comet's ice, the vast majority by mass, remained pristine, untouched by cosmic rays, untouched by stellar heat, frozen in its original configuration since the epoch of formation. When the nucleus fragmented in March of 2020, it was this deep, pristine ice that was briefly exposed to sunlight and began to outgas. The fragments were, in effect, broken seals on an ancient container, releasing material that had been locked away since before the Earth existed. The convergence of evidence was compelling. The extreme carbon monoxide enrichment, the pristine volatile ratios, the deep interior ice exposed by fragmentation, and the thermal models all pointed to the same conclusion. Borisov was experiencing stellar heating for the first time. It was a virgin comet in the most literal sense, born in the cold dark of another star's distant reaches, ejected into interstellar space before ever being warmed, and preserved in cosmic deep freeze until the sun's gravity drew it inward and the sun's light began to melt the seals. If this interpretation is correct, then the chemistry we measured in Borisov's outgassing is about as close to a pristine sample of another star's protoplanetary disk as we are ever likely to get without sending a spacecraft to collect one. The ice was untouched. The record was unaltered. What we saw was what was there at the beginning. A frozen snapshot of the conditions that existed around a distant unknown star at the moment when its planetary system was still being built. Think about what that means for the future of this field. Every interstellar comet that passes through our solar system is potentially a pristine messenger from another planetary system. An unopened envelope, sealed since the dawn of its parent system, whose contents can be read by the warmth of our sun. If most interstellar comets are, like Borisov, making their first stellar approach, then the chemistry we observe is not contaminated by prior heating events. It is original. It is authentic. Each new detection is a clean sample from a different cosmic kitchen. But there is a complication, and researchers were careful to note it. Even if Borisov had never been heated by a star, it had spent hundreds of thousands or possibly millions of years exposed to the interstellar radiation environment. Galactic cosmic rays, high-energy protons and heavy ions accelerated by supernova remnants, and other violent astrophysical phenomena would have bombarded its surface throughout its interstellar journey. These energetic particles penetrate the surface to depths of a meter or more, breaking chemical bonds, creating new molecular species through radiolysis, and gradually transforming the composition of the outermost layers. The surface ice that sublimated first as Borisov approached the Sun may have been significantly altered by this cosmic ray processing. The pristine, unprocessed material lay deeper, beneath the irradiated rind, in the interior that was exposed only when the nucleus fragmented. This distinction between surface and interior ice became critically important when interpreting the chemical measurements. The extreme carbon monoxide abundance could not be explained by cosmic ray chemistry alone. Radiolysis can produce some carbon monoxide from carbon dioxide and water ice, but not in the quantities observed. The enrichment had to be primordial, dating back to the comet's formation. The cosmic ray processing was a complication, a source of noise in the signal, but it did not drown out the underlying message. The message that Borisov formed in an environment dramatically enriched in carbon monoxide compared to our own solar system survived transmission through the interstellar medium with enough fidelity to be read. The fifth and final investigation extended beyond Borisov itself to the broader question of what the detection of two interstellar objects in 2 years tells us about the galaxy. This was not an observational campaign so much as a statistical exercise, an attempt to work backward from the fact that we detected two interstellar objects in a specific time window, using specific telescopes with specific sensitivities and specific sky coverage to estimate the total number of such objects that must exist in interstellar space. The logic was similar to wildlife surveys. If you sit in a blind and count how many birds fly past in an hour, you can estimate the total bird population in the area based on how big your field of view is, how long you watched, and how likely any given bird was to pass through a particular patch of sky. It is a powerful method but sensitive to the assumptions built into the calculation, and different groups made different assumptions. The key inputs to this calculation were the sensitivity and sky coverage of the surveys that detected Oumuamua and Borisov, the brightness and trajectory of each object, and the geometry of detection. What fraction of all possible incoming trajectories would have been detectable given our telescope's capabilities? The results, published by several independent groups, converged on a remarkable conclusion. The local density of interstellar objects in the Sun's neighborhood is on the order of 0.1 to 1 object per cubic astronomical unit. Scaled up to the volume of the Milky Way, this implies a total interstellar object population in the range of trillions to quadrillions for objects larger than a few hundred meters. These numbers were stunning. They meant that interstellar space is not empty. It is a reservoir, vast and dark, filled with the accumulated debris of billions of planetary systems that have formed and evolved and shed their leftovers over the 13-billion-year history of the galaxy. Every star that ever formed planets ejected material. That material has been building up, populating the interstellar medium for cosmic ages, and we are only now, with the advent of wide-field, high-cadence sky surveys like Pan-STARRS and soon the Vera-C, Rubin Observatory, gaining the ability to detect these objects as they drift silently through our cosmic neighborhood. The Rubin Observatory, in particular, represented a generational leap in capability, with its 8.4-meter mirror and its 3.2 billion pixel camera, the largest digital camera ever built. It would survey the entire visible southern sky every 3 nights, to a depth and sensitivity far exceeding any previous survey. Simulations suggested that Rubin could detect 1 to several interstellar objects per year during its planned 10-year survey. Each detection would be another data point, another chemical fingerprint, another message from another star. Over a decade, the trickle could become a stream, but even Rubin has limits. It can only detect objects that come close enough to the sun to be warmed and brightened by sunlight, or that reflect enough light to stand out against the background sky. The vast majority of interstellar objects will never pass through the inner solar system. They will drift past our star at distances of hundreds or thousands of astronomical units, too faint and too cold to be detected by any telescope on Earth or in orbit. We will see only the closest ones, the ones that happen to wander into our narrow cone of visibility. The rest, the overwhelming majority, will pass in silence unnoticed, carrying their alien secrets onward to the next star, and the next and the next. There was also the tantalizing possibility that some interstellar objects might have already been detected without being recognized as such. The distinguishing feature of an interstellar object is its hyperbolic orbit. Its velocity is too high for it to be gravitationally bound to the Sun, but marginally hyperbolic orbits are difficult to distinguish from highly elongated elliptical orbits, especially for faint objects with short observational arcs. Could some of the many thousands of comets discovered over the centuries have actually been interstellar visitors whose trajectories were not measured precisely enough to reveal their hyperbolic excess? Several groups investigated this question by examining the orbital catalogues, and the consensus was that, while no previously known comet could be confidently reclassified as interstellar, the possibility could not be entirely excluded for a handful of cases with poorly determined orbits. This realization added another dimension to the statistical picture. The number of detected interstellar objects, currently 2, was almost certainly a severe undercount. Not only were most interstellar visitors too faint or too distant to detect, but some fraction of those that were detected may have been misidentified as ordinary solar system comets on highly elongated orbits. The true passage rate through the inner solar system could be substantially higher than the naive calculation suggested. The European Space Agency recognized the scientific opportunity early and began developing plans for a mission called Comet Interceptor, designed to wait in space at the Sun-Earth Lagrange Point 2 until a suitable target was identified, either a long-period solar system comet or, ideally, an interstellar visitor, and then divert to intercept it on a fast flyby trajectory. The mission, approved in 2019 and scheduled for launch in the mid-2020s, would carry instruments capable of measuring the chemical composition, dust properties, and physical structure of the target at close range. Exactly the kind of detailed characterization that ground-based and orbital telescopes can only approximate. If Comet Interceptor succeeds in reaching an interstellar object, the scientific return would be transformative. Instead of measuring the composition of a distant, unresolved point of light through the filter of a cometary coma, scientists would obtain direct measurements of the gas and dust at close range, potentially including the isotopic ratios that are the most diagnostic indicators of formation environment. Isotopic ratios, the relative abundances of heavy and light versions of the same element, are set during the molecular cloud and disk phases of star formation and are extremely difficult to alter afterward. They are the deepest, most persistent chemical memories a comet carries. If we could measure the oxygen isotope ratio, the carbon isotope ratio, and the nitrogen isotope ratio of an interstellar comet, we would have a far more powerful tool for identifying its parent system and formation environment than any volatile abundance measurement could provide. The combination of Rubin's survey capability and Comet Interceptor's flyby capability represented a qualitatively new approach to interstellar object science. Rubin would serve as the discovery engine, scanning the sky systematically and identifying incoming interstellar visitors months or years before they reached the inner solar system. Comet Interceptor would serve as the response vehicle, redirecting to intercept the most scientifically promising targets. Together, they could transform the study of interstellar objects from a reactive catch-can enterprise into a planned, systematic scientific program. But even this ambitious vision had limitations. Comet Interceptor could fly by a target, but it could not rendezvous with one, could not match speeds, orbit alongside it, and study it for months or years the way Rosetta studied Churyumov-Gerasimenko. A flyby encounter, however fast and sophisticated, would yield only a snapshot, a brief, high-resolution snapshot, vastly richer than anything achievable from Earth, but still a snapshot. The dream of the field, the ultimate goal that researchers spoke of in conference hallways and speculative papers, was a sample return mission, a spacecraft that could match velocity with an incoming interstellar object, collect material from its surface or coma, and return that material to laboratories on Earth for analysis, with the full arsenal of modern analytical chemistry. Such a mission was technically conceivable but far beyond current capabilities. It would require detecting the target years in advance, launching a fast spacecraft on an intercept trajectory, and solving the formidable engineering problem of rendezvousing with an object moving at 30 or more kilometers per second relative to the Sun. The technology did not yet exist, but the scientific motivation was overwhelming, and the detection of Borisov had given the planetary science community its strongest argument yet for investing in the development of that technology. What Borisov revealed, through these 5 interconnected investigations, was both exhilarating and humbling. It showed that the tools of modern astronomy are powerful enough to identify, track, and chemically characterize an object from another star system in real time. It showed that the chemistry of comets varies from system to system in measurable and scientifically informative ways. It showed that interstellar space is far more populated with wandering debris than anyone had imagined before 2017. And it showed, with uncomfortable clarity, how much we still do not know about Borisov's parent star, about the conditions of its formation, about the degree to which its interstellar journey altered the chemistry we measured, and about the trillions of similar objects that we have never seen and may never see. Taken together, the 5 investigations painted a portrait of a comet that was simultaneously familiar and alien. Familiar in its broad strokes, ice, dust, gas, a fuzzy coma and a sweeping tail, but alien in its details, in the proportions of its chemical ingredients. In the story, those proportions told about a stellar nursery unlike our own. Borisov was recognizable as a comet in the same way a foreign language is recognizable as speech. You can hear that someone is saying something. You can identify some of the sounds, but the meaning, the specific, detailed particular meaning, requires deeper translation than a brief encounter permits. The scientific community had extracted an extraordinary amount of information from Borisov's brief passage through the inner solar system, more, arguably, than anyone had a right to expect from a small, faint, fast-moving object observed for only a few months. And yet the list of unanswered questions remained longer than the list of answered ones. What star did Borisov come from? When did it form? What planets, if any, orbited alongside it in its parent system? Were there other comets in that system with similar chemistry, or was Borisov an outlier even among its siblings? How long had it been travelling? How many other stars had it passed? At too great a distance to be warmed, but close enough to feel their gravitational tug. None of these questions could be answered with the data in hand, and most of them could never be answered. Not for Borisov, and possibly not for any interstellar object in our lifetimes. The messengers arrive, briefly glow, and then vanish into the dark. We read what we can, we archive the data, and we wait for the next one. Then something happened in early 2020 that changed the tone of the entire investigation. In the first days of March 2020, the Hubble Space Telescope captured a sequence of images that would become some of the most discussed in modern cometary science. The images showed Borisov's nucleus in the process of breaking apart. The central condensation, which had appeared compact and bright for months, was now elongated, A secondary brightness peak had appeared, offset from the main nucleus, surrounded by its own small cloud of dust and gas. Over the following weeks, additional observations confirmed what the initial images suggested. The nucleus had fragmented. A piece of Borisov, a chunk of alien ice that had traveled across light years of interstellar void, surviving cosmic ray bombardment and the slow erosion of millions of years, had broken off under the modest thermal stress of our own sun. The event was scientifically valuable, as discussed earlier. It exposed fresh interior ice and confirmed the deep carbon monoxide enrichment of the nucleus. But the fragmentation also carried a deeper, more unsettling significance that went beyond chemistry and spectroscopy. It was a reminder of impermanence. This object, this ancient messenger from a distant world, was not going to survive its visit. It was not going to fly past the sun, recede into the outer solar system, and continue its eternal drift through the galaxy as it had for the previous several 100,000 years. It was disintegrating. Our sun, which gave it the warmth needed to reveal its chemical secrets, was also destroying it. The very act of observation was an act of annihilation. There is a parallel here to quantum mechanics that, while imperfect, captures something true about the situation. In quantum physics, the act of measurement disturbs the system being measured. You cannot observe a particle's position without changing its momentum. You cannot read the information without altering the source. Borisov, on a macroscopic scale, embodied the same cruel paradox. The solar heating that made its chemistry readable was also the force that was tearing it apart. The messenger was consumed by the act of delivering the message, and this was not a slow, gradual process. The fragmentation, once it began, proceeded rapidly. The Hubble images showed the secondary fragment separating from the main nucleus over a period of days. Additional monitoring over the following weeks revealed further structural changes. The central condensation became diffuse, the brightness profile flattened, and the morphology shifted from the tight, compact appearance of an intact nucleus to the looser, more irregular appearance of a rubble pile surrounded by expanding debris. By late March of 2020, it was clear that Borisov's nucleus had undergone significant disruption. The pristine visitor from interstellar space was crumbling before our eyes. Consider the timeline. Borisov formed in a protoplanetary disk around an unknown star, probably billions of years ago, long before the Earth existed, possibly before the Sun itself ignited. It was ejected from that system, perhaps by the gravitational kick of a migrating giant planet, perhaps by a close encounter with another young star in the birth cluster, and began its long drift through interstellar space. For hundreds of thousands of years, possibly millions, it travelled in perfect, undisturbed silence through the coldest, emptiest environment in nature. No heat, no light, no contact with any other body, just the faint hiss of cosmic rays and the dim glow of the galaxy's combined starlight. A frozen time capsule, perfectly preserved, carrying a chemical record of conditions that existed around a young star in an era we cannot date and in a location we cannot name. And then, in 2019, it drifted into the gravitational influence of our sun. The warmth began, the ice stirred. For the first time in its existence, Borisov's surface began to transform. Solid ice turning to gas streaming outward, carrying dust into a glowing coma and a tail that pointed away from the sun like a ghostly banner. For a few months, it was visible. For a few months, human telescopes could study it, and then it began to fall apart. This is not science fiction. This actually happened. A piece of another world's history arrived at our doorstep, briefly flickered into visibility, and then crumbled. And the crumbling was not incidental to the story. It was central. The fragmentation of Borisov was, in a sense, the climax of the entire narrative, the moment when the comet gave up its deepest secrets at the cost of its own integrity. Before the breakup, the carbon monoxide detected in the coma could theoretically have been a surface phenomenon, a product of cosmic ray processing of the outer layers, not necessarily representative of the bulk composition. After the breakup, that argument collapsed. The exposed interior ice was just as rich in carbon monoxide as the surface had suggested. The enrichment was not superficial, it went all the way down. The entire comet, through and through, was made of alien ice in proportions that had never been seen in our solar system. The fragmentation also gave scientists an unexpected opportunity to study the structural engineering of an interstellar comet. By tracking the separation velocity of the fragments, the rate of brightening as fresh ice was exposed, and the evolution of the coma morphology over the following weeks, researchers could constrain the tensile strength and cohesive properties of the nucleus material. The results suggested that Borisov's structural strength was comparable to that of solar system comets, very weak, in the range of a few tens of pascals, roughly equivalent to the strength of freshly fallen snow. The comet was structurally a snowbank that had been drifting through interstellar space for eons, held together by nothing more than the weak molecular bonds between ice crystals and the gentle pressure of its own negligible gravity. The philosophical weight of this fact is difficult to overstate. Borisov was the first interstellar object ever observed in enough detail to reveal its chemical composition. It was, in a very real sense, the first tangible sample from another planetary system that humanity has ever analyzed. Not a light curve, not a blurred photograph, not a spectral line from a distant star, but actual material, actual molecules, actual ice and dust from a place beyond our solar system. And it arrived just in time for us to read its message before it dissolved. Consider how extraordinary that timing was. Humanity has been looking at the sky for thousands of years. We have built telescopes for 4 centuries. We have had the spectroscopic capability to identify molecules in cometary Comet for roughly a century. But the sensitivity to detect and characterize a small, faint interstellar comet, that capability has existed for perhaps 2 or 3 decades at most, with the construction of large survey telescopes and space-based observatories like Hubble. And within that narrow window of technological readiness, an interstellar comet happened to pass close enough to the Sun, at a favorable enough geometry, and with enough outgassing activity to permit a detailed chemical characterization. The coincidence is not physically unlikely. The statistical models suggest that interstellar objects pass through the inner solar system regularly, but it feels, on a human timescale, like a gift that arrived precisely when we had developed the capacity to receive it. There is a concept in information theory called the Shannon entropy of a message, a measure of how much information a signal carries. Borisov's chemical composition was a signal. Its carbon monoxide abundance, its hydrogen cyanide ratio, its dust properties, its fragmentation behavior, each was a data point, a letter in a message written in the language of molecular physics. And the total information content of that message, while far from complete, was vastly more than anything Oumuamua had provided. Oumuamua was a postcard with no text. Borisov was a partial letter, fragmentary, faded in places, missing jizz, but for the first time, we could read, however imperfectly, the chemical autobiography of a comet that formed around another star. And this was not just a scientific achievement. It was a conceptual milestone, a fundamental expansion of what humanity knows about the universe. Before Borisov, every chemical analysis of cometary material told us about our own solar system and nothing else. We could measure the volatile composition of a dozen different solar system comets and compare them to each other, but the comparison was always internal. It was like studying the regional cuisines of a single country. You could identify variations, map the differences between north and south, learn which regions prefer certain ingredients over others, but you could never say whether the entire country's cuisine was typical or unusual compared to the rest of the world, because you had never tasted food from another country. Borisov was the first taste of food from another country, and the flavor was recognizable but distinctly different. Similar enough to be intelligible, different enough to be informative. The same basic ingredients, water, carbon monoxide, hydrogen cyanide, combined in proportions that no solar system kitchen had ever produced. One dish from one foreign restaurant does not tell you everything about that country's cuisine, but it tells you something. It tells you that the ingredients are shared. It tells you that the cooking methods are related. And it tells you, with certainty, that the cuisine exists. That there is a whole culinary tradition out there, beyond the borders you know, waiting to be explored. Let that sink in. For the entire history of astronomy, Every chemical measurement of a comet told us about our own solar system. Every isotopic ratio, every volatile abundance, every dust grain analysis, all of it was self-referential. We were studying ourselves. And then, in the span of a few months in 2019 and 2020, that changed. A single object expanded the scope of cometary science from one solar system to two. One solar system to two does not sound like much, but consider the analogy to biology. For decades, the search for life beyond Earth has been hampered by what scientists call the n=1 problem. We know of only one example of life on Earth, and from a single example, it is impossible to draw general conclusions. Is DNA universal? Is water necessary? Is carbon-based biochemistry the only option? With n=1, we cannot answer any of these questions. We are trapped in a sample size of 1. Cometary science faced the same problem. For centuries, n=1. Every comet was a local comet. Every chemical measurement came from the same pantry. We had no way to know whether our solar system's cometary chemistry was typical, unusual, or wildly anomalous compared to comets elsewhere in the galaxy. Borisov changed n from 1 to 2, and in science, the jump from 1 to 2 is the most important jump of all. It is the jump from isolation to comparison. It is the jump from anecdote to data. This point deserves elaboration because its significance is often underappreciated by non-scientists. When you have one example of anything, you cannot distinguish the essential from the accidental. You see that life on Earth uses DNA, but you cannot know whether DNA is a necessary feature of all life or a historical accident specific to Earth. You see that our solar system's comets have a certain chemistry, but you cannot know whether that chemistry is dictated by universal physical laws or by the particular, unrepeatable circumstances of our solar system's formation. One data point gives you a fact, two data points give you a comparison, and comparison is the engine of understanding. With two data points, our own solar system's comets and Borisov, scientists could begin to ask comparative questions for the first time. Is our cometary chemistry typical? The answer appeared to be, broadly yes, but with significant local variation. Borisov was made of the same basic molecules, water, carbon monoxide, hydrogen cyanide, dust, but in different proportions. The recipe was shared. The seasoning differed. This single comparison, crude as it was, carried implications of enormous scope. It suggested that the chemical building blocks of comets, and by extension, the chemical building blocks of planetary systems, are universal across the galaxy. Water ice is everywhere. Carbon monoxide ice is everywhere. Hydrogen cyanide is everywhere. The raw materials from which planets and comets form are the same, star to star, system to system. What varies are the conditions under which those materials are assembled. The temperature, the pressure, the stellar luminosity, the dynamics of the disk. Here is what makes this truly terrifying. If the molecular ingredients of comets are universal, but the recipes differ, then every planetary system in the galaxy is conducting its own unique experiment in chemistry. Each system takes the same raw materials, the same atoms, the same simple molecules, and processes them under different conditions to produce a different set of complex compounds. The diversity of outcomes is not random. It is structured, governed by physical laws, and potentially predictable if we knew the input parameters well enough. But the sheer number of experiments being conducted simultaneously, billions of planetary systems, each with its own temperature profile, its own disk dynamics, its own timeline of evolution, means that the chemical diversity across the galaxy is staggering, and some of those chemical experiments may produce the precursors to biology. This is not idle speculation. The connection between cometary chemistry and the origin of life is one of the most actively investigated questions in astrobiology, and Borisov's detection gave it new urgency. The argument runs as follows. Life on Earth requires a specific set of molecular building blocks. Amino acids, the subunits of proteins, nucleobases, the letters of the genetic code, sugars, the structural backbone of DNA and RNA, lipids, the molecules that form cell membranes. These molecules are complex, but they are not impossibly complex. They can be synthesized through known chemical reactions from simpler precursors. Reactions driven by ultraviolet light, by electrical discharges, by mineral catalysis, by the high temperatures and pressures of hydrothermal vents, or by the energetic shock of a cometary or asteroidal impact. And many of these precursors have been detected in comets. The Rosetta mission found the amino acid glycine in the coma of Comet 67P. Meteorite analyses have identified dozens of amino acids, nucleobases, and sugar-related compounds in carbonaceous chondrites, which share a common origin with comets in the early solar nebula. Laboratory experiments simulating the conditions of cometary ice, ultraviolet irradiation of frozen mixtures of water, methanol, ammonia, and carbon monoxide have produced complex organic residues containing amino acids, sugars, and other prebiologically relevant molecules. The chemistry is not speculative. It has been demonstrated in the laboratory, detected in space, and identified in meteoritic samples. The question, then, is whether this chemistry is unique to our solar system or universal. If only our comets carry organic precursors, then the relevance to the origin of life elsewhere is limited. But if comets across the galaxy carry similar inventories of complex organics, if the chemical toolkit for prebiotic chemistry is standard equipment in every planetary system, then the conditions for life's emergence may exist essentially everywhere that rocky planets form in the habitable zones of their stars. Borisov did not directly address this question because its distance and faintness prevented the detection of complex organic species. The molecules measured, water, carbon monoxide, hydrogen cyanide, cyanide radical, diatomic carbon, are relatively simple. But hydrogen cyanide is itself a critical prebiotic molecule. It is one of the key feedstock molecules in the Formose reaction, which can produce sugars, and in the Strecker synthesis, which can produce amino acids. Its detection in an interstellar comet at abundances comparable to those in solar system comets was a significant finding. It meant that at least one of the key ingredients for prebiotic chemistry is present in comets formed around other stars, and if the building blocks are universal, then the conditions for prebiotic chemistry, the chemistry that preceded life on Earth, may also be universal. Comets, after all, played a significant role in Earth's early chemical evolution. The late heavy bombardment, roughly 3.8 to 4.1 billion years ago, delivered enormous quantities of water and organic molecules to the young Earth. Some scientists believe that cometary impacts seeded the planet with the complex organic compounds, amino acids, sugars, nucleobases that served as the raw ingredients for the origin of life. If comets across the galaxy carry similar inventories of organics, then the conditions for life's emergence may exist around many, perhaps most, stars. Borisov, of course, cannot answer the question of whether life exists elsewhere. No single comet can. But it provided a data point that was entirely new and deeply relevant. It showed that interstellar comets carry the same classes of molecules, including organic precursors, that are found in our own solar system's comets. The universe's chemical toolkit, it seems, is not specialized, it is general. Now step back farther and consider what the detection of two interstellar objects in 2 years means in the context of the galaxy's history. The Milky Way is roughly 13.6 billion years old. Star formation began within the first few 100 million years and has continued at varying rates ever since. Every generation of stars has formed planetary systems, and every planetary system with giant planets has ejected icy debris into interstellar space. This process has been running for over 13 billion years. The earliest planetary systems, those that formed around the galaxy's first stars, have had the longest time to contribute to the interstellar population. Their comets have been drifting for more than 12 billion years, traveling distances of thousands of light years, passing through countless stellar neighborhoods, each one a potential detector. And the process has never stopped. New stars are forming right now in molecular clouds throughout the galaxy, and the planetary systems coalescing around them will, in a few million years, begin ejecting their own comets into the interstellar void, adding fresh material to a reservoir that has been accumulating since the galaxy's youth. The accumulated debris from all of these ejections, the sum total of all the comets, asteroids, and planetesimals that have been flung out of their parent systems across the entire history of the galaxy, represents an enormous reservoir of material. We cannot see it. We cannot count it. We can only infer its existence from the occasional visitor that happens to pass through our small patch of space. But the inference is robust. The galaxy is filled with the remnants of dead and living planetary systems, all drifting in the dark, all carrying chemical records of their origins. The numbers involved are almost incomprehensibly large. If every star in the Milky Way, roughly 200 to 400 billion stars, ejected even a modest number of cometary bodies during the formation and early evolution of its planetary system, the total population of interstellar objects would exceed a quadrillion. And the Milky Way is just one galaxy among trillions in the observable universe. The total number of interstellar objects in existence, the total number of chemical fossils drifting between and within galaxies across the cosmos, is a number so large that it defeats intuition. There are more wandering comets in the universe than grains of sand on all the beaches of Earth, more frozen messengers than stars in the sky, more chemical records of dead worlds than there are worlds that are still alive. And some of these wanderers are very old. Borisov may have formed billions of years ago, around a star that has since exhausted its hydrogen fuel and evolved into a white dwarf, or exploded as a supernova, or merged with another star in a binary system. The parent system may no longer exist in any recognizable form. The planets may have been consumed or scattered. The disk from which Borisov condensed may have been dissipated for eons, but the comet itself survived. It survived because it was ejected early, before the catastrophe, flung out into the interstellar void while the system was still young, carrying a frozen record of conditions that have long since vanished. In this sense, interstellar objects are fossils, not biological fossils, but chemical fossils, preserved samples of environments that no longer exist, carried across the galaxy by gravity and inertia, waiting to be found by anyone with the instruments and the patience to look. The analogy to paleontology is surprisingly apt. A paleontologist studies fossils, mineralized remains of organisms that lived millions of years ago, to reconstruct ancient ecosystems, trace evolutionary lineages, and understand the conditions that existed on Earth in the distant past. The fossils are incomplete. They are biased toward organisms with hard parts that mineralize well. They have been altered by the geological processes of burial, compression, and chemical transformation, and yet, despite all of these limitations, they provide an irreplaceable window into the past. They are the only direct evidence we have of life forms that no longer exist. Interstellar objects play an analogous role for planetary systems. They are the preserved remains of protoplanetary disks that formed billions of years ago around stars that may no longer shine. They have been altered by cosmic ray irradiation, by internal radioactive heating, by the slow diffusion of volatile molecules through porous ice. But the alteration is limited, especially for objects that have spent relatively short times in interstellar space. The chemical record is degraded but not destroyed. The message is faded but not erased. And, like paleontological fossils, interstellar objects are the only direct physical samples we have of environments that we cannot visit and that may no longer exist. The difference is one of scale. Paleontological fossils come from our own planet's past. Interstellar chemical fossils come from the pasts of other planetary systems. Systems separated from us not just by time, but by the vast distances between stars. Reading a paleontological fossil requires understanding Earth's geological history. Reading an interstellar chemical fossil requires understanding the chemistry of protoplanetary disks around stars of different types, in different galactic environments, at different epochs of the galaxy's evolution. The interpretive framework is incomparably more complex, but the basic logic is the same. Preserved material tells you about the conditions that existed when and where it formed. Let that sink in. We are surrounded by fossils of dead worlds. They drift through the space between stars, invisible and silent, each one a fragment of a planetary system's childhood preserved in ice. And when one of them, by sheer chance, wanders close enough to our sun for its ice to begin sublimating and its coma to begin glowing, we have a brief, precious window, weeks, maybe months, to read the message it carries before it crumbles or recedes into the dark. Borisov was one such window. It opened in the autumn of 2019. It closed in the spring of 2020, when the nucleus fragmented and the comet began its long, one-way journey back out of the solar system, receding into the outer darkness at a speed that will carry it beyond the reach of any telescope within a few years. It will never return. The interstellar void will reclaim it, and it will continue its drift, diminished, fragmented, partially evaporated, for millions of years more, until it encounters another star or dissipates entirely. But the data it left behind endures. Every spectrum, every image, every measurement is now part of the permanent scientific record. And from that data, a picture is emerging, tentative, incomplete, but growing clearer with every new analysis, of a galaxy where planetary systems routinely form comets, routinely eject them into interstellar space, and routinely send them drifting across the light years to be found, eventually, by curious civilizations orbiting distant stars. Whether any other civilization has ever intercepted one of our own ejected comets, a piece of the Sun's Oort cloud, launched into the galaxy by Jupiter's gravitational kick billions of years ago, is a question we cannot answer, but the symmetry is suggestive. If we can detect their comets, perhaps they can detect ours. And if so, the galaxy is not just connected by light and gravity. It is connected by ice, by the slow, silent exchange of frozen chemical messages between planetary systems that will never know each other's names. This vision of the galaxy as a network of icy messengers is profoundly different from the vision that prevailed before 2017, before Oumuamua and Borisov opened our eyes to the interstellar population. In the old picture, planetary systems were islands, isolated, self-contained, separated by vast gulfs of empty space. Material formed in one system stayed in that system. Chemistry was local. History was local. Each planetary system was a closed box, and the only connection between boxes was the photons, the light, that traveled between them. The new picture is radically different. Planetary systems are not closed boxes. They are leaky. They shed material. They exchange debris. Every planetary system that ever formed has contributed to the interstellar population, and every planetary system receives, however infrequently, visitors from other systems. The exchange is slow. Individual objects take hundreds of thousands of years to cross interstellar distances, and the visitors are small, faint, and hard to detect. But the exchange is real, it is continuous, and it has been happening for 13 billion years. The galaxy, in this new understanding, is a single interconnected system, not in the dramatic science fiction sense of warp drives and faster-than-light travel, but in the quiet, patient, physical sense of material exchange. Atoms that formed in one stellar nursery end up in comets that drift to another. Ice that condensed in one protoplanetary disk is delivered, eons later, to the surface of a planet orbiting a different star. The boundaries between planetary systems, which once seemed absolute and impermeable, are actually soft and porous. Material leaks out, material drifts in. Over billions of years, the galaxy stirs itself, slowly, inefficiently, but inevitably, and the chemical products of countless separate planetary systems mingle in the vast, cold reservoir of interstellar space. Borisov was a single drop from that reservoir. One comet, one chemical fingerprint, one brief, brilliant window into the chemistry of another world. But behind that single drop stands an ocean of wandering ice, ancient and diverse, carrying the frozen memories of every planetary system that ever existed, waiting in the dark for the warmth of a passing star to release its secrets. Step back now from the data, the spectra, the orbital mechanics, and the fragmentation images, and consider the full arc of what has happened. In the span of roughly 2.5 years, from October 2017, when Oumuamua was spotted fleeing the solar system, to March 2020, when Borisov's nucleus crumbled under the sun's gaze, humanity went from never having identified a single object from beyond our solar system to having characterized the chemical composition of one in detail. 2.5 years. In the 4.5 billion year history of our planet, in the roughly 300,000 year history of anatomically modern humans, in the 4-century history of telescopic astronomy, this window was vanishingly brief. And yet within it, the entire field of interstellar object science was born, grew from infancy to adolescence, and produced results that will shape planetary science for decades to come. The implications of what Borisov revealed extend in multiple directions simultaneously, and each direction leads to questions that are both scientifically profound and existentially unsettling. The first implication concerns the universality of chemistry. Borisov showed, with hard spectroscopic evidence, that the molecular building blocks of comets, water, carbon monoxide, hydrogen cyanide, organic dust, are not local products of our solar system's particular history. They are general. They exist in comets formed around other stars, in other parts of the galaxy, under different conditions. The ingredients are shared. What differs are the proportions. This finding, if confirmed by future detections of interstellar objects, has consequences that cascade far beyond cometary science. It touches on the question of whether the chemistry that preceded life on Earth, the prebiotic reactions that produced amino acids, nucleobases, sugars, and lipids from simpler molecules, could also occur around other stars, seeded by cometary deliveries of organic material. If comets everywhere carry similar molecular toolkits, then the chemical preconditions for life may be essentially universal. Life itself may or may not be universal. That profound question remains unanswered and may remain so for generations to come. But the chemistry that enables it appears to be standard equipment in the galaxy's planetary systems. The second implication concerns the interconnectedness of the galaxy. Before 2017, planetary systems were thought of as isolated islands, self-contained units of matter orbiting their parent stars, separated from all other systems by the immense, empty gulfs of interstellar space. Each one formed from its own molecular cloud, evolved its own set of planets and debris, and kept to itself. Material did not travel between systems in any meaningful quantity. The interstellar medium was empty, a void separating closed, self-contained worlds. Borisov, along with Oumuamua, demolished this picture. The galaxy is not a collection of isolated islands. It is a network, a slow, patient, gravity-driven network in which material is continuously exchanged between planetary systems over billions of years. Comets ejected from one system drift through the void and occasionally pass through another. Dust and gas shed by disintegrating interstellar objects contribute to the diffuse material between stars. The galaxy stirs itself, mixing the products of billions of separate chemical experiments into a single, enormous, slowly evolving reservoir. This is a fundamentally different vision of the cosmos than the one that prevailed for most of the 20th century. It means that the matter in our own solar system is not entirely homegrown. Some fraction of the material that exists in the Sun's neighborhood, perhaps a tiny fraction, perhaps not so tiny, may have originated in other planetary systems, delivered over billions of years by the same kind of interstellar wanderers that Borisov represents. The atoms in the ice that caps the mountains of Earth, the dust that settles on the rooftops of cities, the water that fills the oceans. Some of those atoms may have traveled here from other stars, carried by comets and meteoroids that were ejected from their parent systems and captured, eventually, by the Sun's gravity. We are not purely local. We are, in some small but real sense, galactic. The third implication concerns the future of exploration. Borisov demonstrated that interstellar objects can be detected, tracked, and chemically characterized with existing technology. The Vera C. Rubin Observatory, expected to detect several interstellar objects per year during its 10-year survey, will transform the trickle of data into a steady stream. The European Space Agency's Comet Interceptor mission, designed to fly by a long-period comet or interstellar visitor, could provide the first close-range measurements of an object born around another star. And further in the future, more ambitious missions, perhaps even sample return missions, if the engineering challenges can be overcome, could bring pieces of interstellar ice back to laboratories on Earth for the kind of detailed isotopic and mineralogical analysis that telescopic observations can never match. Each new detection will be another data point, another chemical fingerprint from another star, another letter in a growing correspondence between our solar system and the galaxy that surrounds it. Over decades, as the sample size grows from 2 to 10 to 50 to hundreds, the statistical picture will sharpen. We will learn whether Borisov's extreme carbon monoxide enrichment is typical of interstellar comets or an outlier. We will learn whether most interstellar objects are icy comets like Borisov or rocky bodies like Oumuamua. We will begin to map the chemical diversity of comets across the galaxy, and from that map, we will infer the diversity of formation environments, the range of temperatures, pressures, stellar luminosities, and disk chemistries that exist across the Milky Way's hundreds of billions of planetary systems. This mapping effort will be, in a sense, the first true census of galactic chemistry, conducted through direct sample analysis rather than remote spectroscopy of starlight. Each interstellar object is a core sample drilled from the frozen history of a planetary system we may never observe any other way. Some of those systems may no longer exist. Their stars may have died, their planets may have been consumed or scattered, but their comets survive, drifting through the galaxy as the last physical remnants of worlds that have vanished. When we study an interstellar comet, we may be studying the only surviving evidence that a particular planetary system ever existed at all. The philosophical weight of this possibility is immense. We are accustomed to thinking of the night sky as a map of the present, each star a point of light, marking a currently burning furnace of nuclear fusion. But the interstellar objects that drift between those stars are messengers from the past. They carry the chemistry of planetary systems that existed millions or billions of years ago, some of which may be long dead. The interstellar medium is, in this sense, a museum. A vast, dark, cold museum of galactic history, where the exhibits are not paintings or sculptures, but frozen chunks of planetary childhood, each one labelled with a chemical signature that encodes the conditions of its creation. This is a new kind of astronomy. Not the astronomy of light, of photons collected from distant objects and decoded into spectra, but the astronomy of matter, of physical material delivered to our doorstep from other worlds, carrying information encoded not in electromagnetic radiation, but in molecular bonds and isotopic ratios and crystal structures. It is astronomy by mail. The galaxy sends us samples, and we analyze them. The delivery system is slow, hundreds of thousands of years per package, but the information content is extraordinarily rich. A single interstellar comet, studied in detail, carries more information about its parent system than can be extracted from years of telescopic observations of that system's star. Consider how profoundly this changes the nature of the conversation between humanity and the cosmos. For centuries, astronomy has been a one-way observation. We look outward, we collect light, we build models, we infer, but we never touch. The stars and planets and galaxies we study are separated from us by distances that make physical contact impossible on any human timescale. We are confined to our small planet, our small solar system, peering at the universe through the narrow window of electromagnetic radiation that reaches us. Interstellar objects change that equation. They are physical matter from other worlds that arrives within our reach. Not within easy reach. We cannot yet intercept one with a spacecraft, though that capability may come within decades, but within observational reach. When Borisov passed through our inner solar system and released its carbon monoxide and hydrogen cyanide and dust into the warming influence of the sun, those molecules became part of our local environment. They mixed into the solar wind. They dispersed into the interplanetary medium. In a very real, very physical sense, atoms from another planetary system were briefly present in the space around our planet. The material gap between us and other worlds, for a fleeting moment, closed to zero. This is not abstract poetry, it is physics. Molecules from Borisov, carbon monoxide molecules that condensed in a protoplanetary disk orbiting an unknown star, possibly billions of years ago, sublimated within our solar system and dispersed into the volume of space that our planet passes through in its annual orbit around the Sun. Some of those molecules may have been swept up by Earth's magnetosphere, or slowed by collision with the tenuous gas of the solar wind, or simply drifted past as Earth continued on its path. The encounter was real. The exchange of matter, however minuscule, was real. And we are just beginning to open the mail. There is also a temporal dimension to this reflection that deserves attention. Borisov formed billions of years ago. It was ejected from its parent system at a time when our own solar system may not yet have existed, when the molecular cloud that would eventually collapse to form the Sun and its planets was still dispersed across light years of interstellar space, indistinguishable from the surrounding galactic medium. The comet that passed through our solar system in 2019 may predate the existence of the Earth itself. It is older than the mountains, older than the oceans, older than the continents. It is older, perhaps, than the Sun, and yet, despite its immense age, the chemistry it carried was legible. The carbon monoxide was still there. The hydrogen cyanide was still there. The ice, though degraded at the surface by cosmic rays, was still structurally and chemically intact in the interior. Borisov was a time capsule that survived not just the cold of interstellar space, but the passage of geological time, the kind of deep time that erases mountains and evaporates oceans and drives entire species to extinction. The comet outlasted everything except itself. There is something deeply humbling about this realization. For all of our technological sophistication, our space telescopes, our interferometric arrays, our particle accelerators and gravitational wave detectors, we are still, fundamentally, passive recipients. We do not choose which interstellar objects visit us. We do not control their trajectories, their compositions, or their timing. They arrive on their own schedule, dictated by the blind mechanics of gravity and orbital dynamics, following paths that were set in motion millions of years before the first human looked up at the night sky. We can only watch, measure, and try to understand. But what we understand is growing. With every detection, with every spectrum, with every orbit calculated, and every volatile abundance measured, the picture becomes a little clearer. The galaxy is not empty. The spaces between stars are not voids. They are archives. Vast, cold, patient archives of frozen chemistry, carrying the records of worlds we will never visit and stars we may never name. And those archives are open to anyone with the instruments and the curiosity to read them. Borisov opened the first page of that archive. The rest of the book is waiting, patient and cold, in the dark between the stars. It is late now. The stars are out, if you can see them from where you are. And somewhere out there, far beyond the reach of any telescope, far beyond the glow of the sun, beyond the orbits of the planets and the distant haze of the Oort cloud, Borisov is still travelling. It is smaller now than when it arrived. The sun's warmth took some of its ice. The fragmentation took more. The carbon monoxide that scientists measured so carefully has been released into space, dispersed into the solar wind, scattered across millions of kilometers of vacuum. The chemical message that Borisov carried for hundreds of thousands of years, the frozen record of conditions around a star we cannot name, has been partially read and partially destroyed. What remains is a diminished nucleus, perhaps a few hundred meters across, trailing a faint halo of dust and sublimate gas, receding from the sun at a speed that will carry it back into the interstellar void within a few years. It will never return to our solar system. Its hyperbolic trajectory guarantees that. The sun's gravity bent its path but could not hold it. Borisov swept through our neighborhood like a traveler passing through a small town on a highway that stretches to the horizon in both directions, slowing briefly, stopping nowhere, and continuing onward into a distance that has no end. By the time the Vera C. Rubin Observatory opens its eyes in Chile and begins scanning the sky for the next interstellar visitor, Borisov will already be far beyond the reach of any instrument on Earth. It will have crossed the orbit of Neptune. It will be heading outward through the Kuiper belt, past the scattered disk, into the darkness that swallowed it before and will swallow it again. Where will it go? Outward. Away from the sun, away from the planets, away from the warmth that briefly woke it from its ancient sleep. It will cross the orbits of Jupiter, Saturn, Uranus, Neptune, each one a milestone on its journey outward, each one a farewell to a planet it will never see again. It will pass through the scattered disk, the Kuiper belt, the inner Oort cloud, and then gradually, imperceptibly, it will leave our solar system entirely and rejoin the interstellar medium, the vast, cold, nearly empty space between the stars, where temperatures hover just a few degrees above absolute zero, and nothing happens for millions of years at a time. It will drift, silently, indefinitely, carrying what remains of its chemical record, degraded now, partially sublimated, fractured and diminished, toward a future encounter with another star in another part of the galaxy at a time so far in the future that our sun may have exhausted its hydrogen fuel and swollen into a red giant before Borisov arrives. If Borisov encounters another planetary system, and the odds over millions of years of travel through a galaxy populated with hundreds of billions of stars are not negligible, it will once again warm. Its remaining ice will begin to sublime. A faint coma may form, a thin tail may stretch behind it. And if, in that distant system, there exists a civilization with telescopes and spectrographs, and the curiosity to look up, they might detect it. They might measure its chemical fingerprint. They might wonder, as we did, where it came from and what it means. They would not know it had visited our solar system. They would not know that a species of carbon-based primates on a small rocky planet had pointed their instruments at this same object and measured its carbon monoxide and tracked its fragmentation and debated its origins in scientific journals and conference halls. That chapter of Borisov's history would be invisible to them, as invisible as its earlier history is to us. The comet carries no record of the civilizations that study it, only the chemistry of the world where it was born, and here is the thought that stays. While Borisov drifts outward from our solar system, other objects, other frozen wanderers from other planetary systems, are drifting inward. They are out there right now, beyond the range of our telescopes, beyond the sensitivity of our surveys, approaching the sun on trajectories that were determined by gravitational encounters around distant stars millions of years ago. Some will pass through the inner solar system in the coming decades. Some will be detected by the Vera C. Rubin Observatory or its successors. Some will be bright enough, active enough, and close enough to permit detailed chemical characterization, and each one will carry a new message, a new chemical fingerprint from a new corner of the galaxy, a new page in the growing correspondence between our world and all the others. The title of this documentary asked a question, and the answer is now clear. Borisov was not what we thought it was. We expected it to be a curiosity, the second interstellar object, interesting primarily for being rare. What it turned out to be was something far more significant. The first chemical sample from another planetary system ever analysed by human science. The first proof that cometary chemistry varies between star systems in measurable, informative ways. The first evidence that the molecular building blocks of planets, and possibly of life, are universal across the galaxy. And the first hint that the dark spaces between stars are not empty at all, but are teeming with the frozen debris of billions of worlds, each fragment carrying a chemical record of its origin, each one a message in a bottle drifting across an ocean of stars. That answer, clear, definitive, and rooted in data, is worth repeating in a different way. What arrived in our solar system in 2019 was not merely an unusual comet. It was the opening of a door between our solar system and every other planetary system that has ever ejected material into interstellar space, a door that had always existed, open, in fact, since the galaxy was young, but that we lacked the instruments to perceive until the 21st century. Borisov did not open that door. It simply passed through it in a way we could finally notice. We are not alone in the galaxy, not in the dramatic, science fiction sense of radio signals and alien civilizations, but in a quieter, deeper, more fundamental sense. We are embedded in a galaxy that is alive with exchange, a galaxy where the frozen remnants of planetary systems drift between stars, where the chemistry of one world can be delivered to another, where the boundaries between here and there, between ours and theirs, are not as sharp as they once seemed. The galaxy connects its planetary systems not through light or radio waves or warp drives, but through ice, through the slow, patient, inexorable drift of frozen debris across the light years, carrying chemical memories of their origins. Every atom in the water you drink was forged inside a star that died before our sun was born. Every molecule of carbon in your body passed through the interstellar medium at least once, drifting between stars for millions upon millions of years before being incorporated into the molecular cloud that collapsed to form our solar system. You are, in a physical and literal sense, made of material that has travelled between worlds. You are stardust, but you are also interstellar dust. Dust that was processed, transported, mixed and recycled across the galaxy long before the Earth coalesced from it. Borisov reminded us of this fundamental truth. It reminded us that the cosmos does not respect the boundaries we draw between systems and stars and worlds. Matter moves, ice drifts, chemistry travels across the void. And over billions of years, the galaxy mixes itself, slowly, patiently, irrevocably, until the line between here and there becomes meaningless. The next interstellar visitor is already on its way. It was launched from its parent system thousands or millions of years ago, long before any human knew to look for it. It is crossing the void right now, moving at tens of kilometers per second, invisible and silent. One day, perhaps in a year, perhaps in a decade, it will cross the detection threshold of a survey telescope and appear as a faint, moving point of light against the background stars. An alert will go out, telescopes will turn, spectrographs will begin their work, and for a few brief months, another window will open, another chance to read a frozen letter from another world. Until then, the galaxy drifts, the ice endures, and the spaces between the stars, which once seemed so empty, turn out to be the largest archive in the universe. An archive written in molecules, carried by gravity, and waiting, with infinite patience, to be read.